Hi everyone, welcome to this video that's going to go through everything you need to know for A-level Physics Paper 2. It's going to be quite a long one, so use the timestamps to find a topic that you want to go through, and thanks for watching. Particles in a gas move in what's called Brownian motion, which has been observed in smoke particles and also in pollen particles. The idea is that smoke particles were seen to be moving even without anything else visibly being near them, and that's due to there being invisible air molecules near them exerting a force on them, moving them left, right, up and down in a random motion, so they're bombarded by invisible air particles and not by the wind or anything else that's there. This can also be viewed in liquids, so pollen grains, which are very small but not invisible grains in liquid, which can be seen to move in the same way. So this leads us on to our assumptions behind gas particles then. So the first assumption we're going to look at is that the particles themselves are infinitesimally small. So what that means is that they have a negligible volume compared to the volume of the total gas or the container they're in. Sometimes that's called point molecules. So the volume is negligible compared to the container. This assumption is that there are no electrostatic forces between the molecules or between the particles. And now if you study A-level chemistry, you'll know a little bit about this, about polar molecules and London forces. We just don't worry about that at all at A-level physics. Particles are moving in continual random motion, so kind of left, right, up, down, different range of speeds, and every collision they are involved in is elastic. So that could be with other particles or with a container wall. That means all kinetic energy is conserved and not lost due to heat, things like that. And our last assumption is that a collision time or time for a collision is very small compared to the time taken to travel from kind of one side of the container to another. This will be really important when we look at a derivation later in the video. Now, integral to the idea of gases is gas pressure. So we're going to look at how is pressure exerted in a gas. Now, this is all about the interactions between particles or molecules and the walls of a container, not each other. So let's say we have a particle with a mass m and initial speed u entering into a container. It rebounds off in an elastic collision and it rebounds with a velocity u. So how would we work out the force that it exerts? Well, we'd use the equation force equals change of momentum divided by change in time. Now, overall, the change of momentum, it goes in with mu, it comes out with minus mu because it's traveling the opposite direction. That gives us a total of 2mu, so the force would be 2mu divided by any change in time. So therefore, that has to be a non-zero value, so there must be a force when the particle hits the container. So in words, what you'd say is pressure is exerted in a gas when there is a change of momentum when a particle collides with a container wall. You could say due to a change in direction of the particle. Therefore, there's a force exerted, and you can quote the equation here. That's always a good idea. And how does that link to pressure? Well, we should know that pressure is equal to force divided by area. So if there's a force on a certain area, therefore there's going to be a pressure by each particle colliding, so an overall pressure on the container. So how can we increase that pressure inside a gas? There are a couple of ways on how to do this. Way number one is to increase the temperature of the gas. So if we increase the temperature of the gas, what that means is that the particles or the molecules have an increased kinetic energy. And this is just talking about particles, not the gas overall. It's not moving anywhere. So increased kinetic energy means more frequent collisions, more collisions per second, and also greater force because the velocity has increased as well. As well as using the temperature to change the pressure, we could decrease the volume. Now, decreasing the volume would mean that there are more frequent collisions because there's a decreased time between collisions. So there's more collisions per second, meaning a greater overall force, meaning a greater pressure because pressure equals force divided by area. These relationships between pressure and other factors are known as gas laws. So the first one, which is the first bullet point here, is how pressure relates to temperature, which is called the pressure law or the Gay-Lussac law. And it says that pressure is proportional to temperature if the volume is constant and the mass of the gas is constant. So if I was to plot a graph of pressure versus temperature in Kelvin, it'd be directly proportional going straight through the origin. Next is the relationship between pressure and volume. So this is known as Boyle's law. So Boyle's law states that we said if you decrease the volume, the pressure goes up. So that means that pressure is inversely proportional to volume if the temperature is constant and if it's a constant mass of the gas as well. So to plot that in a graph, you'd have pressure and volume would look like a curve like this, which you could prove by replotting as pressure is directly proportional to a 1 over volume graph. Now, there's one more gas law you need to know about. That's Charles's law, which isn't to do with pressure, and pressure is constant. Then the volume of the gas is directly proportional to the temperature. And again, we've got the same or constant mass of the gas. So that then gives us a graph of volume being directly proportional to temperature if it's in Kelvin, and volume is usually measured in meters cubed. How can we use these relationships in calculations? Well, volume is equal to a constant times by T, the temperature. Therefore, V over T is equal to a constant. So V1 over T1 initially is equal to V2 over T2 finally. So you should have three of those values, find the missing one by using that relationship. It's the same thing with pressure and temperature. P1 over T1 equals P2 over T2. And pressure and volume, if you multiply them together, that would be a constant. So therefore, pressure 1 times volume 1 equals pressure 2 times by volume 2. Now, combining these three relationships together, we can come up with an overall relationship between pressure, volume, and temperature, which is that if I multiply P by V divided by T, that is equal to a constant. And I can do the same thing here. I can say P1 times V1 divided by T1 equals P2 times V2 divided by T2. Now, this constant does have a value, and we're going to use it in coming up with the ideal gas equation. So PV over T equals N, which is the number of moles of the gas, multiplied by the molar gas constant, which is 8.31, and obviously will be in your equation sheet. So that's the constant there. You'll see this equation usually rewritten slightly differently as PV equals NR times T. This equation only works if pressure is in pascals, volume is in meters cubed, number of moles is in moles, and the temperature's got to be in Kelvin, so add 273 to it if it's given to you in degrees, because absolute zero is minus 273. What if you wanted to find out the overall number of particles in a sample of a gas, capital N? So what you need to know is the number of moles of the gas, and then you need to know how many particles are in 1 mole. Now, this number is Avogadro's constant, which you should recognize from GCSE or A-level chemistry, and it's given by 6.02 times 10 to the power 23. Now, rearranging it, we can then say the number of moles is equal to the number of particles divided by Avogadro's number. So I can replace the N, a small case n, in the ideal gas equation with those two terms. What we might notice is I've now got two constants in my equation. So I'm going to draw out the capital N and have those two constants divide by each other. So R over NA times by T. Now these two constants divide by each other. 8.31 divided by 6.02 times 10 to the power 23 equals 1.38 times 10 to the power minus 23. And this is a constant known as Boltzmann's constant. So it gets its own name, gets its own symbol, which is the letter K. And again, it's on your equation sheet. You just got to make sure you reach the right equation with the right constant at each time. So this one you use if you want to know the number of particles or your given number of particles. So these two equations together, PV equals small case n R times T and PV equals capital N times KT, are known as the ideal gas equation. So you're given them both, make sure you know which one to use in each instant. Now there can be an extra twist, which is questions involving molar mass, which is going to really take you back to GCSE chemistry if you're not studying A-level. Molar mass, as the name suggests, is essentially the mass of 1 mole of a substance, which will be different for different substances. So for example, 1 mole of a mass would be 12 grams of carbon-12. On the other hand, it would be 32 grams of oxygen-16, because oxygen it has 2 atoms in a molecule, giving you a total atomic weight of 32, so it'd be 32 grams. Okay, so notice the pattern here. The way we define it in terms of physics is we say it's the mass of 12 grams of carbon-12. That's because carbon-12 is an incredibly stable isotope, so we've used that for the last couple of centuries to define what 1 mole weighs. So we use that to define what the mass of 1 mole is. So using this expression and the molar mass m, if I wanted to find that out, I'd need to know the number of moles and the total mass of the substance to find out the mass of 1 mole. So if I know the number of moles and I know the mass of the overall substance, I can divide them to find the molar mass. So why is this useful? Well, if I have the molar mass, I can use it to find out the number of moles. So the molar mass of a substance is equal to the total mass divided by the number of moles. Now, then I can use this if I wanted to put it into my ideal gas equation and say number of moles equals the mass of the substance divided by the molar mass. That can tell me n, so I can input it into my equation. So that little expression is not given to you in your equation sheet. My top tip is to try and look at units if you can. So the molar mass is in kilograms per mole. So so mass divided by number of moles. So it'll help you keep an eye on, well, what is it and how do I find the number of moles or moles to put into my equation. Next, what we're going to look at is one of the hardest derivations you could find in year 13 physics, but it comes up and it's good use of applying different parts of physics and the topics to ideal gases. So we're deriving this expression here. Let me talk about that last term, CRMS. Now, if I try and find the average velocity of a bunch of particles, no matter what speed they're going at, because they're all going in different directions, their velocity average will equal 0 because they'll all cancel out. So we use a different type of average called a root mean square speed. Now that comes up in magnetic fields when you look at kind of current and RMS voltage as well. How you work it out is you square the values, then you add them, then you find the mean, then you square root. So you kind of do what it says there, but do it in reverse. So you square it, then you mean it, then you square root it. So our derivation, we're going to consider a sample of a gas moving, one particle moving first of all, and we're going to try and derive this equation. So follow along each step, get your pen and paper ready, and let's dive in. So this particle has a mass m and has initial velocity u. So as we covered briefly before, the force of a particle when it hits a wall will be equal to 2mu divided by t. Now, once we consider that first particle, we are only considering one direction. However, let's say we have a three-dimensional container like a cube, we have to consider 3 dimensions. So the number of particles we're talking about is only a third of the overall particles that are in that container because we're just considering one direction. So we say n over 3 times by our expression for the force 2mu over t. Now, I'm going to draw out that 1 over t for reasons I'll explain in a second, and everything else stays the same. Let's combine the n over 3 with the 2mu together. So the 1 over t is going to become important because we're going to look at how to work out the velocity of the particle. So let's say the length of the cube is L, the time taken, so speed equals distance over time, time equals distance over velocity, the distance travelled between one side of the cube and the other is 2L over V. Rearranging this for 1 over t, I flip the fraction, it becomes V over 2L. So therefore I replace this into my value from earlier for 1 over t. So therefore I've got V over 2L times by my expression from earlier, 2m u divided by 3. All right, I hope you're following along so far. That's the bulk of the work done for now, and you'll be pleased to know. So what we're going to do is just combine those expressions together. I've got 2v, so I've got v squared, and I've got 2 on the top and the bottom, so those two cancel, and I've got force equals nm v squared divided by 3l. So in the derivation, we're trying to look for pressure. Now, pressure equals force over area. Now, the area of the cube, the length is L, so the area is L squared. So force equals pressure times by length squared. So I'm going to substitute that instead of the force on the left-hand side, and the right-hand side stays the same. But we can simplify things down because I've got L squared on one side, and I've got L on another. So if I divide both sides by L squared, now I've got 3L cubed on the bottom of my expression. Now, L cubed, we should know, if I've got length times length times length, that's the same thing as saying the volume of the cube. So therefore, I can rewrite it, P equals nmv squared over 3 times the volume, capital V. Rearranging a little bit, and now I've got PV on one side, a third on the other side, and instead of V squared, I'm just going to use that expression RMS speed squared, but nothing's really changed apart from that, and that's the derivation for that equation. Now, some questions can be really sneaky and ask you about or ask you to calculate the density of a gas. So how do we involve density in this expression? Now, we know density is mass over volume. Now, little m here is the mass of a molecule, and then n is the number of particles. So the total mass of the gas is given by capital M times by little m, the mass of one molecule. So if I bring the volume expression over to the right, I've now got density equals mass over volume. Now, what's remaining in the equation is we've got a 3 over to the other side, 3p over root mean squared speed. So that's how you could find the density if you're given, for example, the pressure and the speed. Okay, final derivation for this one is the last expression you'll find in your equation sheet, which is looking at this equation on the right hand side here, which is that the average kinetic energy, half mv squared, is equal to 3 over 2 kt, where t is the temperature of the gas and k is Boltzmann's constant. So we're going to use our ideal gas equation from earlier and the equation we've just derived, combine them together to prove this is the case. So you notice we've got PV on both equations, so we can then equate together the right hand side. So nm root mean squared speed squared equals nkt. So the first thing we should notice is I've got an n on both sides, so I can cancel that later nice and easily. That's straightforward. It's the same capital N for both. And if I multiply both sides by 3 over 2, I have the same expression as on the right-hand side of the thing I'm trying to derive, which is 3 over 2 kt. Now, multiplying the left-hand side by 3 over 2, 3 over 2 times a third is going to cancel down to 1 over 2, which is the half we're looking for, m times by root mean squared speed over 2, root mean squared speed. Now, this is the average kinetic energy of a molecule. So you could be asked this question and you could be given the mass and the root mean squared speed, or you could be given the temperature. Either side of the equation is both the average kinetic energy of a molecule. However, the right hand side is easier to use. Now on the equation sheet, it also has it R over NA, just means the same thing, means K, the Boltzmann constant. We can use that to find the average kinetic energy. Now the first thing we're going to define today is what is a field, in particular a gravitational field. Now, this definition applies to electric fields as well. You just have to tweak a couple of words. We'd say a gravitational field is a region around an object of mass where another mass experiences a force. So without mass in both objects, there's not going to be a force between them. That's key to understanding gravitational fields. Now, what about field lines? These things I've drawn here acting towards the object. So field lines would show the direction a mass or a test mass would take when placed in that field. So here, the mass is going to go towards the planet, indicated by the arrow shown on the paper. Okay, next definition we're going to look at is particular to gravitational fields. We're going to look at gravitational field strength, which we use a small case g to define. It's defined by this equation here. So G equals F over M, which you might recognize from year 12 is the same as basically weight equals mg, just rearranged. So it's one of those definitions we can use an equation to help us with. So defined in words, it is force per unit mass, not just force per unit mass, but acting on a small mass placed in a field or a gravitational field in this case. Yeah, we should know G for planet Earth is equal to 9.81. So that's in newtons per kilogram using this equation. It also has units of meters per second squared if you're talking about acceleration due to gravity. So next, let's talk about different types of fields. So most of the mechanics you've done prior to this topic will have been based around things happening close to the surface of the Earth. For example, people throwing an object or things on the scale of meters. So 5 meters, 10 meters, etc. And now there are different types of field. Now this type of field, which you've come across already, is different to the one you see on the left. The one on the left is called a radial field. And this one I've just drawn here is an example of a uniform field. So uniform in physics normally means constant or the same. And in this case, it means G or field strength is constant. Whereas for a radial field, G changes with distance. We'll look at how that happens shortly. But the further away you go, G does actually decrease. Now, when you're close to the planet, the surface of the Earth, we can actually assume that the field is uniform, even if it's actually not. Now, the reason is because obviously the Earth is round, it's curved. When you get very close to it, it's almost practically a straight line. So for all intents and purposes, it is uniform. However, if you climb a mountain or a really high hill, you will notice G can change slightly. Now, there's a lot of equations in this topic, so we're going to make a note of them in the bottom right of the screen, just so we can see how they all link together a bit later on. So let's move on to Newton's law of gravitation, a really fundamental law developed by, guess who? Isaac Newton. And it's one of those laws that was measured first before it was kind of formulated. So it was done using measurements of stars and planets in the night sky. And it describes how two masses interact. And it says there's a force between these masses. And the force between the masses depends on two things. First of all, it depends on, and it's always attractive, just to note down here, it's never repulsive. We haven't found repulsive gravity. It doesn't fit into our thinking yet. But those forces are proportional to the masses, so which kind of makes sense. If you have a heavier planet, you're going to have a greater force between them. It's proportional to the mass of both objects. It's inversely proportional, so meaning it goes up if this goes down, to the distance between two objects or between the two masses. Now, in particular, it's not just inversely proportional to that, it's inversely proportional to the square of the distance between them, hence known as an inverse square law. In particular, it's the different distance between the center of masses of those shapes. Okay, so let's start formulating this into an equation. In algebraic form, F is proportional to M1 times M2. So we're going to rewrite that expression for masses, and we say it's proportional to the product of the masses. So the two masses multiplied together. And putting those things together, we get an equation that looks like this. So F equals capital G, M1, M2 divided by R squared. Sometimes you see capital M and lowercase m. It's the same thing. Now, this value G is a constant. It's been measured to be 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Now, that's been empirically measured. It's pretty small, which usually indicates that the force, gravitational forces are very, very small almost always. Now, the relationship works like this. If I double the distance, force gets quartered. If I double the mass, the force doubles as well. Okay, let's come back to gravitational field strength. So we defined this earlier as force per unit mass, or F over m. Now we've got an expression for F. We're going to use this to come up with another expression for gravitational field strength. So this value F here, we said it equals to gm1m2 over r squared. So if I rewrite this whole thing, it's really helpful in this topic to know where the equations come from, even though obviously you don't need to memorize them. So if you divide that whole expression by m, one of the masses is going to cancel. That's the mass of the object, or the thing that's orbiting the larger mass. And we are left with 1m gm over r squared, where that m that's left is the mass of, like, for example, the planet or the sun, whatever is the field we are measuring. So G equals big G m over r squared is our value for gravitational field strength. Now, let's look what a graph of this would look like. If I was to have G and R on the x-axis, what would the shape of the graph be like overall? So we're going to have a look at the relationship. We said earlier, F is inversely proportional to R squared. It's the same with G. So our graph looks a bit like this. And the dotted line there would be the radius of the Earth. So it's at its maximum, 9.81. However, I said at the start of the video, what if you would dig a hole? What if you were to go deeper and deeper inside the Earth so that the radius actually decreased? Well, interesting things start to happen there. Because let's say you're at this random point. You would have mass of the Earth on different sides of you. So some on the left, some on the right, some below you, and some above you. So those, the effect of those forces will actually start to cancel out. And if you're right in the center, you'd have equal amounts of mass on all sides, meaning you're effectively weightless. You wouldn't be able to get out. You wouldn't fall through to the other side. You just stay there forever and ever until someone was able to drag you out, meaning that's when you actually have 0 G. So how to explain this mathematically? Because it is pretty cool, but you can prove it if you use our expression for gravitational field strength. So inside the Earth, G equals capital G m over r squared. But assuming it's uniform density, which is not, but it's an assumption we can make here to generalize, which is density equals mass over volume. The volume of a sphere is 4 over 3 pi r cubed. So if we substitute the expression for mass in, which is density, times that volume, we'll notice actually the r squared on the bottom can cancel with the r cubed on the top, leaving us with G equals 4 pi times by the density times by r over 3. So that then gives us the relationship G is proportional to r when inside the Earth's surface, or when r is lower than the radius of the Earth. So our next bit of our graph looks like this, meaning G goes to 0 linearly when the radius of the Earth has been gone below. The next thing we're going to look at is gravitational potential and potential energy, which are two really important concepts to define carefully. Okay, definitions are usually worth one, definitely 2 marks, and it's really important you can define them to be able to use them in equations. So we'll talk about potential energy first. Now, normally when we've talked about potential energy in year 12 or at GCSE, we're throwing objects up, something gains gravitational potential energy because it gains height. Now, if you were to take this to the extreme, if you were to throw something really, 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 really far, okay, in a uniform field, then it must have infinite potential energy the further it gets, if it gets to an infinite distance, okay? So because work done equals force times distance, therefore, we can then say the force is going to be infinite as well on that object, which doesn't really make sense, okay? So what we then do is we say, well, if you've got a planet or an object where I'm throwing an object away from it, the force has to kind of decrease the further away it got, because we've said force is proportional to the inverse of the square of r. So those two things are pretty kind of contradictory at the minute. So how we get around that is we say that potential energy must increase with distance. However, it must be 0 at what we say infinity. Okay, when they're infinitely far away, it has to be 0. So how we get around this is we say gravitational potential energy values must be therefore be negative. Okay, because if they're negative, they can get higher, i.e. closer to 0 the further away you go, but then they eventually do reach 0 if you go to infinite distance. So the definition for gravitational potential energy is the work done moving an object from infinity to a point in a field or in a gravitational field. Really important to say that word infinity. You could say energy required instead of work done, but work done is easy enough to remember. Next is the one that people always get mixed up on is gravitational potential. Now, gravitational potential is very similar to the idea of potential difference when we look at electric fields, and it's defined in a very similar way, but note the slight differences here. So it's defined as work done per unit mass. So work done per unit mass in moving a object from infinity to a point in the field. So definitely one to commit to memory because it is one that's really, you can't really imagine it. It's one of those things you've got to define with that definition and with an equation. So in equation form, this is given to you in your equation sheet. Potential capital V equals minus gm over r. It's negative for the same reason we just mentioned. Potential energy is negative. Now, if I wanted to work out the potential energy, that is work given by work done equals mass times by the potential, or potential equals work done per unit mass. We just talked about that equation. So in the AQA, you do have to derive it. So therefore, it's going to equal gm over r times by m, which is gm small case m over r. That's potential energy or work done. And the big M we're talking about here is mass of the planet, as opposed to mass of the object. Okay, so do make sure you can derive that one easily. If you're doing AQA, so it's not given to you on the equation sheet. Okay, so as we mentioned before, these are always negative, these values. You'll find negative graphs, and it's just one thing to remember. The negative isn't anything to be afraid of, just as how we define it, with infinity being at zero energy. So let's make a note of how some of these different equations can relate together, because we've got one more to derive. So G equal little g gravitational field strength equals gm over r squared, and potential equals gm over r. So using those two equations, we can actually see that G equals the potential equation divided by R, meaning that would be an R squared on the bottom. And this is the last relationship, which is that gravitational field strength is equal to the potential gradient, or the change in potential divided by R, meaning that would be the gradient of a VR graph. So really important in this topic is that you can link together different equations together. You obviously don't need to memorize them, but it does help to know where they've come from, so that you can answer questions involving graphs and when you've got different values given to you. So I'm going to take an example here. So work done equals gmm over r, and force equals gmm over r squared. So we know that work done equals force times distance. We're going to say r here. So actually work done being force times distance, our equation for force times r cancels the r squared, becomes r, which is the expression for work done. So it's one of those ways you can see how two different equations link together, so that you can help solve graph equations, which come up a lot in gravitational and electric fields. Like this one here, let's say I've got potential and how it varies with R. It's negative, and I'm asked to calculate G, gravitational field strength. So here that's going to equal the gradient, because G equals V over R. What if I was asked to find, this time for a force distance graph, if I was asked to calculate the work done? Or it could be gravitational potential. So what I'd do in that case, I know that work done equals force times distance. So in a graph, that represents the area between 2 points, between two R's. So I can use the area to work out work done, divide by mass if I'm trying to find potential. So let's finish off this topic talking about two different derivations that come up. Let's start with escape velocity. So the idea behind escape velocity is if I'm standing on a planet, let's say planet Earth, and I throw an object off, what is the minimum velocity needed for it to escape the Earth's gravitational field? You can't just say to escape gravity, but escape the Earth's gravitational field, i.e. when G would equal zero. So what we do in this case, we say, well, let's think about energy. As I throw it up, it's going to be losing kinetic energy, it's going to be slowing down, it's going to be gaining gravitational potential energy. So if I write down both those equations, and I'm assuming there's no air resistance, in this case, however much kinetic energy it loses, it's going to gain gravitational. So the equation for work done, or GPE, is going to be equal to gmm over r, deriving that by using potential. We know kinetic energy equals half mv squared. So I'm going to balance those two equations out. We're going to do some cancelling. One of the m's cancel, and I'm going to solve for v. So v squared in this case is 2gm over r. And then for v, I just square root the whole thing, which is pretty nice going. You don't need, you do need to know how to get there for this equation. It doesn't get given to you in the exam. Now, as well as this, you could be asked to express it in terms of small case g, gravitational field strength. So g equals big G m over r squared. So in this case, what that means is I could replace one of the r's to the left-hand side, and I could say, okay, gm over r equals r times by field strength. Therefore, I could replace those in my value to give root 2gr. Now, if I plug in the values for planet Earth, for mass and for radius, I get escape velocity of around about 11,000 meters per second, which is pretty high. Now, if I'm a rocket taking off from the Earth, I do not need to reach that velocity. A couple of reasons for it, mainly because they're burning fuel, meaning they are adding extra acceleration to their journey. So it's not just an initial velocity, they're also losing mass as they get higher and higher for the same reason, which is really good news for the space industry. Right, last derivation we're going to do is called Kepler's third law. and it relates to objects orbiting a planet. So we're going to consider a satellite here. It could be objects orbiting a star as well, but we're going to talk about planet here. And the relationship, Kepler's third law says that the time period squared is proportional to the radius of orbit cubed. So where on earth does that come from? Well, let's consider an object going in circle around a planet, and we can consider the forces that are acting on it. So sometimes exam questions will tell you that, sometimes you might be expected to just know that straight away. So we start off with the centripetal force equation, which is mv squared over r from the circular motion topic. We say that's provided by gravity, so therefore that equals capital G mm over r squared. Let's cancel some of the little r's and one of the r's and r squared, and gives us an equation v squared equals capital G m divided by r. So we're talking about an object orbiting with a velocity. Now we're going to have to get time period into this equation. How we do it is we say velocity equals 2 pi r over the time period. And we've got to square that whole expression. So therefore 2 squared is 4, pi squared, etc., r squared, and we divide by t squared equals gm over r. Now, once we've got to that point, it's just rearranging carefully. You should be able to spot the r times to the left-hand side here gives us r cubed. So 4 pi squared r cubed equals gmt squared. I'm going to divide the right-hand side by 4 pi squared to give me that whole expression in brackets. Now, it's really important to notice we've proved that r cubed is proportional to t squared, but only because all those are constants. G is a number, the mass of the planet is the same, 4 pi squared is just a number as well. So there we go, that's how we derive that relationship. Now, how to use it is, let's say I've got two satellites at different distances, different r's away from a planet, and basically we are trying to find out what the time period is. So for each object, r cubed over t squared has to be constant. So in that case, therefore, r cubed of A divided by t squared of A has to equal r cubed of B divided by times squared of B. I think that's the easiest way I would go about doing it. You could find constant proportionality, but it will be the same thing. Now, electric field strength is a definition that's very similar to gravitational field strength. It's defined by saying the force per unit charge on a positive charge at a point in an electric field. So we can define this using an equation. Electric field strength, capital E, is equal to F over Q, or force per unit charge, given in newtons per coulomb. Let's have a look next at some different types of field you can get. So we can come across uniform fields and radial fields. Now, unlike gravitational fields, uniform fields do exist in electric fields. They're not like an assumption because of the geometry of the Earth. So in a uniform field, we've got two plates parallel to each other, and the field has these kind of uniformly spaced lines between them. In a radial field, that's due to there being a point charge or a spherical charge with the fields pointing radially outwards. And the idea is that the field shows, or field lines show, the direction in which a positively charged particle or a positive charge will move. So in this diagram on the left, it's going to go down, be attracted towards the negative plate. On the right, it's going to be repelled away from my point positive charge. Now, because it's uniform, we say the field strength in our uniform field is constant, and it's given by the voltage, or PD, divided by the distance between those two plates. So an alternative unit for electric field strength is volts per meter, Vm to the -1. Now, we could also say this instead of positive and negative, could just be a difference of 200 to 100 volts. As long as there's a difference or potential difference, this formula still works. For radial fields, we need to talk about Coulomb's law, which talks about the forces between two charges. And we assume they're point charges here. And if I've got one positive and one negative, they're going to be attracted towards each other. They're going to exert a force towards each other. So we defined Coulomb's law is defined by saying the forces between two charges are proportional to not just the charges themselves, but the product of two charges. So that's Q times by Q for the two different charges. It's also inversely proportional to the square of the distance between them, or the distance between them squared. Now, for point charges where there's negligible volume, that's just the distance between them. If they do have a volume, it's between the center of those two charges, or the center of masses of the objects. So combine those two relationships together, we get the overall equation. Coulomb's law is given by the two charges, Q1 times Q2, divided by the distance between them squared. And the constant of proportionality here is a little bit of a mouthy one. Now, it's 1 divided by 4 pi epsilon 0. Now, epsilon 0 is a constant. It's called permittivity of free space. And the number is given by 8.85 times 10 to the -12. Now, some courses will give you the value k instead and say k equals 1 over that 4 pi epsilon 0, which is 9 times 10 to the 9. AQA doesn't. You've got to quote the whole thing, basically. So electric field strength is given by force per unit charge. So dividing that whole equation by charge, one of the Q's is going to cancel, the R squared is going to go to the bottom, and we have another expression for electric field, which is 1 over 4 pi epsilon 0, charge you're talking about, divided by R squared. Now, as charges can be positive or negative, that means that electric field strength and forces values can either be positive or negative. Now, that indicates they have a direction, so it means they are vector quantities. So they can point towards a charge or away from a charge, depending whether it's positive or negative. So that's a difference between electric fields and gravitational fields, which are only attractive. Okay, let's define electric potential then. So electric potential, similar definition to gravitational potential. It's only defined using this, which is to say it's the work done per positive charge or per unit positive charge, i.e. 1 coulomb, moving a positive charge from infinity to a point. So the idea is, same as for gravitational fields, if it's going from infinity, that it's 0 at infinity, moving it into a point is going to be how we define gravitational potential. And the reason we do this is because F has to be 0 at infinity. F can't be getting bigger the further away you go, so therefore potential has to be 0. So to be increasing, if we talk about it getting further away, then it gets closer to 0, while increasing, meaning at 0. At infinity, it kind of makes sense of both those facts. So potential is work done per unit charge. Rearranging, it gives us Q times by potential difference. Similar sort of equation to gravitational fields, apart from Q instead of M. And we can also talk about equipotentials here. So equipotentials, we are talking about, the clues in the name, equipotential, equal potential, points on a surface, or it could be a line, depending on if it's 2D or 3D, that link together places of the same potential. The idea is they're kind of similar to things like contour lines in geography or on maps. When you've got lines linking on a map, the same places of the same altitude, this time it's just areas of the same potential. So when we draw these onto uniform fields, let's draw on our field lines between two plates, and let's give the values to each plate. Let's say one of them has got a voltage or PD of 400, and the other one is going to have a PD of 0 volts. If I was to draw on equipotentials, what it means is that at equal intervals, let's say halfway, we've got a potential of 200 volts. If I was to go between there and 400, we're going to have 300 volts, and the bottom one is going to be 100 volts. Notice the shape is perpendicular to the field lines, and it kind of curves out at the end because the field lines curve out at the end for a uniform field. If I was to draw the same thing for a radial field, again, I've got my field lines going away from a positive charge. Now, keeping the same rules, they're going to be perpendicular to the field lines, and they're going to form, therefore, kind of concentric rings. Assume my field lines are a little bit more evenly drawn. Now, they get further apart the further away they get from a charge. Now, that's because potential is inversely proportional to distance. So meaning they can get further and further spaced apart, even for even intervals of potential. So using an equation for our uniform field, we can rearrange the one from earlier and say, well, potential therefore equals field strength multiplied by distance. For our radial fields, the equation for potential is equal to 1 over 4 pi epsilon 0 times by Q, the charge of the object, divided by R, hence where we get our inverse proportional relationship from. So combining the equation for electric field strength, so 1 over 4 pi epsilon 0, and we got Q divided by R squared, and we can find the relationship between those two things. We can say the field strength is equal to the potential divided by R, or the change in potential divided by change in R. And that's known as the potential gradient. And we could be asked to work out from a graph. So let's have a potential and distance graph. Let's say potential is negative. We're trying to find electric field strength. We find the point, find the tangent at a point, and we work out the gradient. Because field strength is Q over R squared, whereas V is Q over R. If I was asked to find the work done from a force distance graph, I'd find the area between those 2 points, or I could find the potential from that as well, because force times distance equals work done. So lastly, we're going to do a comparison, very quick comparison between gravitational and electric fields. Because if you can learn one, you can kind of learn the other one, basically. There's a couple of differences. Gravitational fields can be attractive only. There's no such thing as negative gravity in our current understanding. Electric fields can be attractive or negative. For gravitational fields, they have positive masses, and electric fields, you can have positive or negative charges. But basically, every equation you learn about for electric fields, you can basically substitute out the charge and you get the same equation with a different constant for gravitational fields, like Coulomb's law of attraction and Newton's law of gravitation. Field strength, we've got, I've done a capital E instead of a small case g here, equals F over m or F over q. And potential is work done over charge or work done over mass if you're talking about gravitational fields. You might find capacitors in these kind of situations. So camera flashes in defibrillators, so to restart someone's heart or to regulate the rhythm again. And they're designed to be used in those situations because they release a large amount of energy really quickly. They're also used in things like timing circuits where timing's important. And when a power output is not constant, they can often be used to smooth out power output when needed. Now in a circuit like this, when I've got a voltmeter across the capacitor and an ammeter, if I was to measure the potential difference versus the charge, and charge in this circuit I do by measuring the current, assuming it's constant, by the variable resistor times by the time, we'd find they have a directly proportional relationship. Now if I found the gradient of that line, that can tell me the capacitance. So the capacitance we define as the charge per unit potential difference. So in equation terms, that would be capacitance C equals Q divided by V. Now the unit for the capacitance is the farad, named after Michael Faraday, or measured in farads. Quite often you'll see these in micro, milli or nanofarads. It's quite a small unit, usually because the amount of charge stored in 1 volt is quite small. A graph of charge and potential difference allows us to calculate the energy stored. Now, the overall general equation for energy stored or work done is equal to charge times IPD, which will be represented by the area under a charge PD graph. And now in this case, our area is going to be a triangle. So the equation for the area of a triangle is half times by charge times by PD. Now we can substitute in our equation for capacitance, so C equals Q over V, in a couple of different ways to get a couple of variants of this equation. So the first one is that energy is equal to VC times by V, or half CV squared, and the next one is equal to half Q, and substituting for V, Q over C, which gives us half Q squared over C. Now sometimes it'll be really obvious which of those equations to use. However, in some situations they might give you lots of different information in a question, so how do we work out which one to use? Now, just like you would do with a SUVAT equation, you've got to look for what you're given in a question and what you're trying to find out. Now, the capacitance of a capacitor is almost always going to be constant in questions like this, but for a equation where you've got the capacitor connected to the cell, the potential difference across the capacitor is going to be constant because it's getting the potential difference from the cell, let's say 6 volts. However, if you were to disconnect it, the potential difference might not be constant, but the charge will be, because as we'll look at later, the electrons will remain in place, so the charge will be constant. So in that case, we'd use half Q squared over C. So let's look at how a capacitor works then. Now you have to be really, really careful with your language here in terms of how you're describing how it works, and make sure you understand it, because it does help make sense of some of the equations we use later, if you can understand what is actually going on with the capacitor charging and discharging. So we'll deal with charging up first. So let's say I close this switch. I've got a very simple circuit with a cell and a capacitor in it. As soon as I close the switch, electrons experience electrostatic repulsion or are repelled away from the negative terminal of the cell. That means in this case they're going to go sort of clockwise around the circuit, sort of away from the cell towards that first plate. Now it's important to note that the capacitor has a gap or an insulator between the two plates, so they cannot cross that point, so therefore electrons will accumulate or sort of build up on one side of the capacitor. Now this makes it a negative plate. Important to note, it's not negative to begin with, it's only got a negative charge because those electrons have started to build up there. Now at the same time, the reverse happens on the right hand side of this circuit. So that means that electrons that are near the positive terminal of the cell are going to have electrostatic attraction this time. So they're going to feel attractive force from the positive side of the cell, which means they're going to go towards it. So in this case, they're going to go continuing clockwise, but around the other side. So note how they're not crossing the gap, but these electrons are already in the wire. They are now going towards the positive terminal of the cell. So what that means, with an absence of electrons on the other side or the other plate of the capacitor, because electrons have been attracted towards the positive end of the cell, they're also repelled away by those other electrons building up. An absence of electrons means you have an overall positive charge. The positive charges haven't moved, they're just what's left behind once the electrons have started to leave. So therefore we have our two plates, one charged positively, one charged negatively. This is how it's able to store charge. So that means I can take away the cell. I don't need it anymore. If I've charged up my capacitor, it's stored a charge already. I could connect it to a bulb or a motor or something like that, and it would be able to, the electrons will go around the circuit as it discharges, and it'll be able to provide electrical current, electrical power to whatever you put there as well. And it sort of acts a bit like a cell. So let's have a look at discharging. Now, discharging would be across a resistor, usually quite a high resistance resistor, and basically the reverse happens. The electrons will go back round the original way. There's a potential difference driving them round. So this will go anti-clockwise, meaning that the potential difference across the capacitor would decrease to zero over time because the charge is decreasing to zero across the two plates. Next, what we're going to look at is what graphs of, first of all, current and time look like for a discharging capacitor. So in this case, obviously I need an ammeter in the circuit to measure the current through the circuit. But really important to note is just if you've understood the explanation previously about how the electrons move, we should note that the current, the rate of flow of electrons, is highest at the start. This is because that's when there's the greatest potential difference that's going to sort of drive them around the circuit. So it'll be the highest at the start, meaning that the current is going to be highest at the start. And the graph follows this shape here, which is exponential decay, which we'll look at a bit later. The reason the current is so low later is because as the capacitor charges, the electrons will receive overall less of a potential difference overall than they were previously. If it gets close to 6 volts across the capacitor, they're going to be slightly attracted towards that, slightly attracted towards the cell, and therefore they kind of balance out a little bit. Now, if we look at a graph of potential difference in time or charge in time, the graphs look a bit different. Now, potential difference has to start off at 0. If I'm going to put a voltmeter across my capacitor, it has to start off on 0 because it's just two pieces of metal initially, and it's going to increase over time. And the shape is actually the inverse of the current time graph. And that's because current is highest initially. So as a high current, that means that the increase in PD is going to be highest initially as well. Now, because PD is proportional to charge, the charge time graph looks exactly the same. I know the curves are slightly different there, just because I'm drawing them quickly. They should look identical for a charging circuit. Now, the equation or the expression to calculate the potential difference at any point or the charge at any point looks a bit like this. So when we're trying to find Q or V at any time t, R here is the resistance, C is the capacitance. We'll come on to what the time constant is a little bit later. But the important thing to note is that V0 or Q0 here, this isn't the initial voltage or the initial charge, because that would obviously be 0. It's the maximum potential difference or maximum charge that the capacitor can hold or can store. Now let's look at a discharging circuit. It's probably the one you would have done for a required practical. It's much, I'd say, more likely to come up in exam questions. So definitely worth learning both. But this one, it comes up in a required practical. It's worth learning this especially. So here's the circuit we'd use. We've got a capacitor with a voltmeter across it, discharging across a resistor. If you want to have a circuit to do both, you can see the circuit I'm drawing here. If you are able to switch the flying lead to the left-hand side, that then charges the capacitor next to the cell. And then if you charge it to put it to the right-hand side, you disconnect that bit of the circuit and you can measure the potential difference across the capacitor as it discharges across the resistor. So the current time graph for a discharging capacitor looks exactly the same as it was before, and the reason is exactly the same. The idea is it's got 6 volts across it. There's no volts anywhere else in the circuit. Once the circuit is complete, the electrons are going to want to be driven by the potential difference to go around the circuit, so the discharge happens really quickly at the start with the highest rate of flow of charge. Now, the potential difference follows the same pattern for this graph. It's going to be highest at the start. It's going to follow that exponential decay downwards. That's because in this case, the voltage is proportional to the current, and the Q is proportional, the charge is proportional potential difference as well. So, like I said there, this is exhibiting something called exponential decay, which you might have come across if you've done the radioactivity topic as well. So what does that mean? Well, exponential decay means anything that follows this form of equation. All these equations follow the same format, but this time I0, Q0, and V0 is the initial potential difference or charge or current, whatever you're talking about. Okay, so we're going to derive one of these equations or show you where it comes from. You never asked to derive the full thing, but I think it's interesting to look at where it comes from. So let's start off with our definition for current. So current equals potential difference over resistance. We said earlier C equals Q over V, so therefore V potential difference equals Q over C. So I can substitute that in and get I equals Q over RC. Now for a very small change in charge, so an infinitesimally small change in an infinitesimally small amount of time, we can have, so delta Q is equal to I times delta T, or Q equals IT, and it's going to be negative, so therefore, because it's a decrease in charge. So what we then have, if I substitute in my expression for I from above, I now have delta Q equals minus Q over RC times by a change in time. Now I can rearrange this equation a little bit to find the rate of change of charge, so delta Q over delta T, and that equals minus Q over RC. Now, as we talked about earlier, R is resistance, C is capacitance, which are both constants. You're not changing those in this circuit. So what that means is that the change in charge over time is proportional to the amount of charge there is remaining, which is the definition for something that shows exponential decay. So basically, the less charge there is remaining, the less the rate of change of charge will be, or the less the current will be. To be able to prove this from a graph like this, if it's just an exponential decay graph, you just go across, you'd find the amount of time it takes for it to halve, for example, and then do it again to quarter, to eighth, and you should find it's the same amount of time to halve each time, therefore proving it's exponential. Now you can make the same arguments for potential difference and for the current graphs, because the two things are proportional to each other. Now we don't really talk about half-lives here with capacitance, unlike in radioactivity. We usually talk about time constants. Now, time constant equals R resistance times C capacitance. You might find it uses the symbol tau in some exam boards, not in AQA. And what it means is when the time equals to RC, the time has passed is equal to the time constant. That means we're going to have T over RC is equal to 1. So therefore, our expression is I equals I naught, the initial current, times by e to the power minus 1. Now, that e to the power minus 1 is about 0.3678, something like that, which rounds to 37%. So that means one time constant is the time taken for the current or the potential difference or the charge to fall to 37% of its original or its initial value. Now, it's quite useful to look at here. How can we prove that time constant's measured in seconds? So I've got resistance times by capacitance. Let's express R in terms of V over I and capacitance in terms of Q over V. We should see the V's cancel here, giving Q over I, which rearranges for time, which is in seconds. So it kind of makes sense that those things all equal out in our equation. And normally for time constants, to measure in a practical, you're going to want something in the order of sort of hundreds of seconds to allow you to measure a reasonable amount of readings on our circuit. A really common form of type of question you could get given doesn't give you V or V naught, but they'll give you an expression like, 20% of it is remaining or 5% of it is gone. In that case, it's really important that you divide V by V naught, and then you can have V over V naught equals e to the power minus T over RC. That should be missed the C out there for some reason. And then that expression is 0.2. So you don't need to know both to be able to answer a question like that. To be able to plot a graph and find the time constant graphically, like in the required practical, we need to take natural logs of both sides. So I can get down the index from Euler's number and use it and actually work it out. So that gives us ln V, a natural log of V equals ln V naught minus T over RC. Now I'm going to rearrange this slightly to get into the form y equals mx plus c if my ln V is my y-axis and t is my x-axis. In that case, I then have ln V equals minus 1 over RC times by t plus ln V naught, meaning that gradient for my graph is going to be equal to minus 1 over RC. So that I can rearrange that and find the time constant. And usually I can compare that in the practical to the value it was if I multiply R times C and see how close it was. Next, let's talk about the capacitor itself. What would an ideal capacitor look like to maximize its capacitance? So they're quite small to put in circuits. Also, they need to be in a camera flash. The ones you've used in class are normally about the size of sort of a finger or a thumb. And they wrap together the two plates really tightly together. The idea is to have the maximum area of overlap between two plates and have the minimum distance between them. So we have quite a thin insulator between them. And they also have to have a really effective insulator between them, which is usually called a dielectric. And we'll come on to what those are usually made of and how they work a bit later. So the equation for capacitance involving those parameters is C equals the area of overlap in meters squared times by the permittivity of free space times by relative permittivity, all divided by the distance between these plates. So you show those relationships to be able to answer questions about this. Permittivity of free space is a measure really of how easy it is for an electric field to form. It's a constant on your equation sheet, 8.85 times 10 to the minus 12 farads per meter here. Relative permittivity is a bit of a new one. So relative permittivity, we can define a couple of ways. My best way is to define it like this. It's the capacitance with the dielectric in place divided by the capacitance with no dielectric, just with free space between the plates. Now, obviously, if you're putting a dielectric in, you're supposed to be improving the capacitor. So let's say you've improved it, have given it a capacitance twice as big as it was originally, then the relative permittivity would be 2. If you made it 100 times better, 100 times the capacitance, then the relative permittivity would be 100. It's just a number. You generally want good capacitors. We're talking about the dielectrics you put in there, like quartz or something like that, hundreds, 400, 500 times better than if there was just free space. So let's look at how do dielectrics work. These can be quite tricky. There's a little bit of chemistry involved as well to explain exactly how they make a capacitor better. So the general idea is we actually want there to be less of an electric field formed than there is without any dielectric in the space between the two plates. So you want an electrically insulating material. We use something called polar molecules. So polar molecules, if you do A-level chemistry, you'll know all about them. If you don't worry. They just have a positive and a negative end due to the distribution of the electrons. That's all we need to know really for this part of the physics course. And now what they do, they will align. Once you switch on the circuit with the capacitor in it, they will align so the negative charges line up with the positive plate and the positive charges line up with the negative plate. So when this happens, you actually manage to reduce the electric field strength of each plate. So that's capital E. Now in a uniform field, electric field strength is potential difference divided by the distance between the plates. Distance is constant, so that means potential difference has dropped as well. Now, if you remember, the definition for capacitance was charge over PD. If I drop the potential difference, that means my capacitor has gone up. The capacitance has gone up, meaning I've made a better capacitance. So the PD stored decreases, meaning the ratio of Q over V has increased, meaning there's a higher capacitance. So what are the basics of magnetic fields? Now, you will be familiar with this diagram here. The magnetic field lines around a bar magnet or a permanent magnet travel from north to south. We can see this by using iron filings or by plotting compasses and placing them around the edge to see their direction. So this is for permanent magnets. We are much more concerned at A-level with magnets that are caused by currents flowing through a wire. So if I've got some current flowing through this wire here, I can find the magnetic field shape around it by using something called the right-hand grip rule. As you can see from the diagram, the magnetic fields form a circular pattern. And if the wire is traveling in the direction that your thumb is traveling on your right hand, then your fingers curl in the direction of the magnetic field. So if I go clockwise or anti-clockwise, if you're looking in the direction of your thumb, they go clockwise. You kind of have to see this yourself with your own right hand. So current is your thumb, fingers are the magnetic field. Now, using both these types of magnetic field, we can explain the motor effect. So let's say I've got a permanent magnet, I've got a north and a south pole, and between it, I've got a wire with a current flowing through it. Now, it's important to note here that the current is conventional current, so we're assuming it travels from positive to negative, even though we know electrons don't do that. So we've got this magnetic field around the wire in this circular pattern we've just seen, and we've also got the magnetic field going from north to south. Now, the magnetic fields, basically the two magnetic fields interact with each other. Now, they essentially overlap. Using the phrase interact is one that comes up on A-level mark schemes. But the reason we're interested in why that happens is because it causes the wire to move, because it causes there to be some force on the wire. So if I was looking at a definition for the motor effect, I would say something like a current carrying wire placed perpendicular to an external or another magnetic field will experience a force. Now, that force depends on a couple of different factors, which you may remember from GCSE. That depends on the current, the magnitude or size of the current flowing through the wire, the length of the wire, and also the size of the magnetic field, the magnetic field strength. Now, we commonly call this magnetic flux density, which will be an important definition when you look at electromagnetic induction and things like that. So because force depends on those three factors, if we multiply them together, we've got the current I, the length of the wire L, and we've got the magnetic flux density, the symbol B. All the units should be straightforward other than the Tesla. So Tesla is the unit for magnetic flux density, and that is equal to, if you were to rearrange this equation, it's force divided by current times length, which means 1 Tesla is equal to 1 Newton per meter per amp. One thing to note at this point is the orientation of the wire relative to the magnetic field. So we said in our definition there's perpendicular. So you have a force, it doesn't have to be perpendicular. So if you view it from above, we've got the wire kind of perpendicular to the field lines, so right angle between them. That's when the maximum force would be experienced. So the maximum force is when the angle between the field lines and the wire is 90 degrees. There'll be zero force if they're parallel or the angle is 0. Anywhere between 0 and 90, there'll be some force, which, depending on the orientation of the field lines or the wire and the angles you're given, you will have to resolve using trigonometry, sort of cos or sine, to find the component that is perpendicular to the field lines. Okay, so to find the direction of the wire, direction of the force on the wire, we can use the fantastic Fleming's left-hand rule, which I've put a picture in here because I'm not going to try and draw the left-hand rule properly. So what it says is I've got my thumb, my index finger, my first finger, and my middle finger. It says that if I've got my first finger lined up with the field from north to south, my second finger lined up with a current from positive to negative, so a conventional current, my thumb will point in the direction of the force. So in this case, for my diagram, field's going left to right, current's going towards me, so therefore my force of my wire is going to go up. If I was to reverse the current, keep everything else the same, that means my thumb is now pointing upwards, so therefore it's going to move upwards. Now, having the motor effect, having a wire move up or down, is kind of cool, but not particularly useful. So using an electric motor requires things to be spinning or moving. So, for example, an electric drill in a food mixer, or the wheels on an electric car. The idea is we want current to change into some form of circular motion. So you can drive something and use it for all those different uses. So to make a motor out of the motor effect, we need a coil of wire for reasons which I'll explain in a moment. So we've got a coil of wire, so not just a piece of wire. Now we have to connect that to a circuit because we want the current to be flowing through it. So I've got a little cell down here with current going from positive to negative, meaning for my coil of wire, the current is flowing up the right-hand side and down the left-hand side as shown. Now, because we've got a current flowing in opposite directions on each side of the coil, that means each side of the coil will experience a force in the opposite direction due to Fleming's left-hand rule. So in this case, do you remember before I had the current flowing towards me? That means my thumb is up, that means it's going upwards, and the current away from me means the wire is moving down. So this will cause it to spin, or there'll be a resultant moment exerted on the wire on each side of the coil. Now, the special name for this, if I've got a moment acting in one direction and another moment acting in the opposite direction, but in the same rotational direction, we call that a couple. So, that will happen to cause the wire to rotate. However, we need something called a split ring commutator to make it carry on spinning. So what this does is it reverses the current every half turn or every half rotation. So that means that the right-hand side keeps going down. Otherwise, it's going to go up, then down, up, then down. It's going to oscillate. We don't want that to happen. We want the right-hand side to keep going down. So the current needs to flip every half turn. So that keeps happening. And it does cut out where the gaps are, but the coil is already moving, so the momentum keeps it going, and so it doesn't stop. So that's the motor effect dealt with. Now, the motor effect can be further explained in more detail by looking at the charges inside the wire. Now, it goes without saying, if the electrons experience a force, then because there's so many of them all going in the same direction inside the magnetic field, that's actually what's causing the wire to move. So because the electrons are charged, they experience a force in a magnetic field the same as the wire does in general, but it's also true of individual charges. And that only occurs when the velocity of electrons is not zero, so when they're moving. So that explains why there has to be a current flowing for this to happen. Now we can derive a quite neat equation for the force on each individual charge. We start off with BIL. Instead of current, we say current is the rate of flow of charge, so delta Q over T, or just Q over T in this instance. So therefore, force is now going to be equal to B times by charge over time times by length. We can also express the length slightly differently. Now, if we consider the length of one piece of wire that's in our magnetic field, we consider the electrons moving along. Now, their velocity, we could say, is equal to the length of the wire, or the distance, divided by the time. Rearranging this for length or distance, we have distance equals velocity times time. So we could replace that instead of the L. And we might notice things become a little bit simpler. So what we can notice is that we've got two terms of T, one on top and one on bottom of a fraction, which cancel quite nicely, gives us F equals BQV, where B is the magnetic flux density, Q is charge, and V is velocity in meters per second. So, like we talked about before, the factors that affect the velocity for one charge is the flux density that affects it, it's the charge that affects it, it's the velocity that affects it. This only occurs when velocity of the charges has a component perpendicular to the magnetic field. F is zero, force is zero when the two are parallel. F is also zero when it's not moving or there's no charge. So it won't work with neutrons and it won't work with any particles that aren't moving to begin with. So how we represent this with diagrams is to look at a magnetic field. In this case, the crosses represent the magnetic field being pointing into the page. Again, this is quite hard to visualize sometimes because it's 3D, but this is the easiest way of doing it. Let's say I've got a proton with a velocity moving into the magnetic field with an initial velocity v. So what's going to happen when it goes into the magnetic field? It experiences a force perpendicular to its velocity. So therefore, the velocity of the proton moves kind of in the upwards direction. Now, again, it experiences a force at each point. So its velocity is changing in a kind of circular manner. So because there's a force that's perpendicular to it at each point. Now, building up those over time, we'll see the path of the proton essentially is starting to form a curve or a part of a circle. Now, note here the velocity doesn't change. The force is perpendicular to the velocity and also perpendicular to the magnetic field. That's why you have to be really careful to think in 3D for these examples. So the particle is now moving in circular motion, which we'll come back to why that's important a little later. We can also use Fleming's left-hand rule to determine the direction on our particle. And we can use Fleming's left-hand rule as it is for protons, because current, we said with the second finger, is conventional, meaning it is assuming that particles have a positive charge or moving positive to negative. Now, we know they're not, but that's the way the rule works. So we can use it as it is for protons. We've got the first finger is the field, the current is represented by the second finger, and the thumb represents the force, which direction it's going to move in. However, with electrons, because they have a negative charge, we have to flip the current finger or the second finger into going the other direction. So it kind of goes sort of logically that if I reverse the charge on our particle here, in this example, the electron is now going to move downwards. It's going to experience a force in that direction, so it's going to curve in the opposite direction to the proton. And this is also kind of helpful when we look at the early days of particle physics, looking at how the cloud chambers identify particles. You have a magnetic field. How do you know whether something's an electron or a positron? Well, you look at the track and see which way it turns, and that would identify the particle for you or help you identify it. Now, as I mentioned earlier, these charged particles are showing circular motion. So just like with gravitational fields and electric fields, anything exhibiting circular motion, we can apply the ideas of centripetal force to them. So what we're going to do is equate together the force experienced by a charge due to the magnetic field with the centripetal force. So we've got BQV on the left-hand side of our equation here. We've got mv squared over r on the right. Now that's going to help us derive an expression for the radius of the orbit, basically how tightly curled the orbit is of the charged particle. So we cancel the v, the squared of the right-hand side and the v of the left-hand side, and we can rearrange this whole thing for r, which gives us r equals mv over bq. Now this quite neat derivation is not on the AQA spec as an equation. It comes up quite a lot in terms of how to derive it, and it also tells us a couple of things about the orbit of these different charged particles. So this is proportional to the mass and the velocity of the particles, assuming, and so it tells us a couple of important things about the orbit of these particles, which is that the radius of orbit is proportional to the mass and the velocity, and inversely proportional to the field strength and the charge. Now, one other sneaky thing questions can ask you to do is to work this out, make this derivation in terms of specific charge. So specific charge is the charge per unit mass of a particle. So essentially, I've got Q and I've got M in this equation. I just need to rearrange that whole equation so that Q over M is the subject. And if I do that, I end up with V over BR. Magnetic fields are essential to understanding all modern particle accelerators. So some of the earliest particle accelerators were linear, and they use electric fields to help accelerate particles. But we've got a couple of recent inventions, talking the last kind of 4 or 5 decades, that are called cyclotrons and synchrotrons, which work in a circle. They all use magnetic fields to help bend particles' path to keep them going in a circle. And now particle accelerators, the whole idea is to get particles to be really fast, so they can either be used in applications like medical purposes or to smash into each other, like in the Large Hadron Collider, and find out things about particle physics. So we're going to look at cyclotrons today. They're the most interesting in terms of magnetic fields, and these are the ones you'd find used in hospitals and used to make radioactive isotopes and for proton beam therapy and things like that. So these two parts of the cyclotron are called Ds, kind of as the name suggests, they shape like Ds, and they've got a magnetic field applied. In this case, we're going into the page or into the screen from your point of view. Particles start off in the center. I'm going to start off with a positive particle, and we apply an electric field between those Ds, between those two areas of magnetic fields. So the particle initially is going to be accelerated kind of across the gap, and that's going to happen a few different times, which will come across one stage at a time. Particle is attracted to or feels a kind of attractive force to the negative plate and therefore accelerates across the gap, getting faster. When it's in the first D, just as we looked at earlier in the video, we've got a force exerted on it, which is going to make it travel in a kind of curve, in a circular motion until it kind of reaches the edge of the D again. So when it reaches the end, it's curved round, and it's going to experience that electric field again. Now, the electric field switches at this point so that it's now got a positive, the positive part of the field is where the particle is located, and it's going to get accelerated across the gap because the negative field has now changed to the other D. Next, it's going to do the same thing. It's going to curve around and then cross the gap again, where the charge flips again to being negative on the opposite side, and then go to the other side, and the same thing happens again and again and again. It's accelerating between the gap, and it's getting its direction curved inside the Ds, so that by the time it reaches kind of the edge of the spiral and hits the target, whatever the designated target is, it's going to be traveling a lot faster than it was initially. So we've got here our equation from earlier. The radius of orbit of the particle is equal to V over BQ. And it states the faster the particle is going, the larger the radius of orbit, which is why the spiral continues getting bigger and bigger each time. Now, in this case, the mass of the particle isn't changing, the field isn't changing, and charge isn't changing. So those are all constants. We can work out the time taken for one rotation or one sort of orbit of the particle around the circle using our equation from earlier. We're going to substitute in, instead of v, the speed equals distance over time, which is 2 pi r over one time period. So instead of v on the top here, we've now got 2 pi r over t. So simplifying this expression further, I've got the expression r equals 2 pi r m over t bq. Rearranging for t, because that's what we're trying to find out, the time for one rotation. We've got an r on the top and the bottom of this expression, so that can cancel, giving us overall the time for one rotation is equal to 2 pi m over bq. And just as well as time period, we can work out the frequency, which is 1 over t, which is the flipped over fraction, which is bq over 2 pi m. Now, important things to notice about this is that the time taken for one rotation is independent of the velocity of the particle and also r. So it doesn't mean how big the spiral is getting. The particle is going to take the same amount of time to do one rotation as the smallest kind of radius in the middle. And this is really useful. It's really fundamental to understanding how these particle accelerators work. Because the time period or frequency is constant, it means that this electric field can be alternating at the same frequency. So it can flip the exact same amount of times when the particle crosses the gap. It doesn't matter on the particle's speed or radius. It can change direction with a constant time period or frequency, for example, 100 hertz. It doesn't need to change. Let's look finally at mass spectrometers. So these are used in chemistry a lot. They're used to identify different elements or isotopes in a sample. We're not going to look too much at what they're used for because you have to take chemistry A-level for that. We're going to look at the physics of how they work. So to start off with, we've got a sample. Usually it's in a gas form and it's ionized. So initially, meaning it's going to have all of the particles are going to have electron ripped off them, meaning they can be positive. So therefore they can be deflected by electric and magnetic fields. So we've got our positive ions in a stream here, or a beam of positive ions. And now we're going to travel through two parts of our mass spectrometers. The first one is called a velocity selector. Now, as the name suggests, that's going to select particles of a certain velocity to continue through to the next stage. It does this by applying an electric field and a magnetic field at the same time to the particles, which I'll explain how that works in a second. So in this case here, I've got the electric field, it's got a positive part on the top of the particles, a negative part on the bottom, and we've got magnetic field is pointing into the page in this example. So the particles are going to experience, those positive ions are going to experience a force from each field. Now, if they were to be affected too much by the electric field, they will, because they're positive, go towards the negative plate. And using Fleming's left-hand rule, if they're affected too much by the magnetic field, they get deflected upwards. So they have these two forces up and down, meaning that just those particles that are traveling at just the right velocity or the certain velocity can get through and not be affected too much by either of those fields. Now, to be exact about it, we can equate the expression for magnetic field, the force for a magnetic field, BQV, with the force from an electric field, which is EQ, E capital E being electric field strength. So equating those two things together, we've got a charge in both sides of the equation, which means it kind of cancels down nicely. To give us the velocity we're talking about here is equal to the electric field strength divided by the magnetic field strength or magnetic flux density. This has only happened because you've got the force going upwards of the magnetic field and downwards of the electric field. Only particles traveling at just the right speed get through that gap. So why are we bothering to do all this? Why are we bothering to select a particle of a certain velocity? Well, when we look at the second part of the mass spectrometer, this time I've got magnetic field, which is pointing out of the page, indicated by circled dots here. And we're going to come back to the idea of the radius of the particle's orbit being given by mv over bq. Now, in this equation, we've got the particles having the same magnetic flux density or field strength, because they're all in the same magnetic field. They all have the same charge, they're all similarly ionized at the beginning. But because they've all got slightly different masses, they're going to move to slightly different places and have slightly different radius or radii of orbit. But this only works if the velocity is the same. So the fact they've only got the same velocity, it only occurs because we've had that velocity selector process beforehand to make v constant, so that the mass is proportional to r, or the radius of their path. So the idea is that the tighter or the lower the r is for smaller mass particles, and the higher the r is for higher mass particles. So if we have a detector located just at this point here, we'll be able to detect how many of each particle goes through, and our results would look something like this. They'd be in a graph form. You'd have certain isotopes go further, certain isotopes less far, and they can figure out what's in our sample. So in this setup here, what we've got is a wire or a conductor moving through a magnetic field indicated by the north and south poles here. When we do that, we get a reading on an ammeter, which measures current. So the definition for electromagnetic induction would be something like when a conductor moves relative to a magnetic field in the perpendicular direction, there's an EMF induced. Now, EMF stands for electromotive force, which hopefully you've covered in year 12. This EMF is induced across the two ends of the conductor. Now, where does the current come from? Well, once there's that potential difference or electromotive force, the electrons will move, which is a current. So the current will flow only if the conductor is connected to a circuit, because we need a complete circuit for current to flow. Now, one thing to note is that the conductor moves relative to a magnetic field. It can be the other way around. You can have a magnet moving inside a coil of wire, like this little setup here. It's the same thing, exactly the same effect, just a slightly different setup. So what factors affect the size or magnitude of the EMF induced? Number one is the speed of the conductor's movement. You move it faster, you're going to have a greater EMF. Number two is the strength of the magnetic field. And number three is the number of turns on the coil. The direction of the electromotive force reverses if the motion is reversed. So if I was to move it up, the current would flow one way. If I was to move it down, the current would flow the other way. I could also flip the poles over. That would have the same effect. Now, in basic terms, and you won't get any marks for this, but in basic terms, to understand roughly what the EM induction is, it's basically the opposite of the motor effect. So the motor effect, current goes into a device with a coil of wire and a magnetic field, and you get motion out, the thing moves. EM induction, the generator effect, is basically the opposite. You move a conductor in a magnetic field, you'll get current coming out if it's connected to a circuit. So it really helps kind of understanding those two things, how they're linked together. Now, the full and the proper physics explanation, again, will make more sense if you see my magnetic field video, because that will explain how does magnetic fields affect charges. Now, we looked at how they affect one charge. However, in a wire, obviously the charges are confined. There are billions of them. They're confined to a wire. So in this example here, we've got a wire moving to the right in a magnetic field that's pointing into the page. That's what the crosses indicate, or into the screen from the way you're looking at it. So using Fleming's left-hand rule, and bear in mind we've got negative charges, so our current finger goes the opposite direction, there's going to be a force on those electrons going down. Now, if there were free charges, they would curve like this. However, because they're in a wire, they can't do that, so something different has to happen. So electrons will experience a force due to the magnetic field. They'll all move in the same direction. This won't be a curve because they can't, they're confined to the wire, so they'll all just go down. Now, that produces our potential difference, or is called electromotive force on the electrons, and leads to current flowing, which is what electromagnetic induction is. Right, to really tighten up our definition of this, we need to look at something called Faraday's law, which really helps kind of tie the whole topic together. So Faraday's law says that the induced EMF in a circuit is equal to the rate of change of flux linkage throughout the circuit. Now, the one word in there, one phrase you won't recognize unless you've studied this intensely, is what flux linkage is, magnetic flux linkage. So let me define magnetic flux first, then we'll look at what flux linkage is. So magnetic flux, which uses the symbol phi, is the product of magnetic flux density by the area swept out by the circuit, by the coil of wire which you're moving through it. So flux density we came across previously, which has the symbol B, measured in Tesla, area is in meters squared, Magnetic flux has the unit Weber, or it's German, so it technically should be Weber, given by the initial WB. Magnetic flux linkage is given by the symbol n phi. That's just one symbol. It's not n times by phi. That's the product of magnetic flux. So phi we just looked at, and the number of number of turns on the coil that you're investigating. So in this example here, let's say we've got a coil wrapped sort of in a circular motion. We've got 4 turns on the coil. Now, if we were to kind of move it through a magnetic field, so the magnetic field here is going right to left, and move it through the magnetic field, it will sweep out the area enclosed by that circular loop. So that will be the area swept through by the conductor. And in this case, it's got 4 turns, so we just multiply that area in meters squared by 4. Alternatively, magnetic flux density, if you've ever wondered why it's called magnetic flux density, well, density is mass over volume. In this case, it's not something over volume, it's flux over area. So flux per unit area is the way we might define magnetic flux density. In terms of an equation for Faraday's law, we can represent it like this. So EMF, kind of curly epsilon symbol, equals the rate of change of flux linkage. Flux linkage is n phi. And because it's rate, it's divided by a change in time. We've got delta on the top and bottom there to represent the change for both. Negative sign we'll come back to in a moment. So where does this equation come from? Well, the derivation is pretty neat, and it comes from the definition for potential difference or for EMF. So imagine the setup for the derivation is I've got those same electrons as before traveling to the right in a magnetic field. This time they're connected to a loop. As they travel in this direction, the electrons would go down on the right-hand side, and the left-hand side, they go up, so it kind of forms this complete circuit, the electrons flowing all the way around. So starting off with that general definition for EMF or for potential difference, it doesn't really matter in this case, is work done per unit charge. Now, as this coil moves through the magnetic field, you're exerting a force on it, so the work done is equal to force times by the distance moved. Now, another way of expressing the force, because it's force on the wire, is equal to B flux density times current, I times L. And it's a change in distance because we're moving it through the magnetic field. Now, on the bottom, we can replace the charge with I times T because we know charge equals current times time. Again, one last parameter to introduce is that the length of the wire in the magnetic field, so either the left or the right-hand side of the coil, we can represent by the symbol L. So cancelling down a couple of symbols, we can see we've got current on the top and the bottom, so we can cancel those down quite nicely. And the last thing we can figure out is that the length of the coil times by the distance it goes through, S, is equal to A, the area. So instead of L times by delta S, we can now replace that. So we've got B times by the area, divide by delta T, or the change in time. Now I've got B times by A over delta time, and we just said that was equal to magnetic flux. So we're talking about one coil here, that will be just magnetic flux, which is given by the symbol phi. So we can just rewrite it simply. And if we did have more than one coil, we just times it by the number of coils. So that's where the Faraday's law comes from. And again, we'll talk about the negative symbol a little later. Now, we could stop our derivation almost towards the end and come up with a slightly different expression. So BL times by the change in distance over the change in time. If we rearrange that slightly differently, I've got change in distance over change in time is also known as velocity. So I can also express Faraday's law as B times by L times by velocity. This isn't on the AQA data sheet, but you could be asked to derive it or use it in the same way we just did the previous one. So where does that negative sign come from in Faraday's law? Well, it's all to do with something called Lenz's law, which is absolutely essential to understanding how electromagnetic induction works. So Lenz's law says, and be careful with this definition, you need to know the word perfectly, that the direction of the induced current, or EMF, is always opposing the change that caused it. Now, that's a bit wordy. You need to know that word perfectly, but let me explain it because it's important you understand it. Let's say I've got a coil of wire down here. I'm moving a magnet in towards it. Now, we know there's going to be a current induced. It can either go in this direction with a positive on the left, negative on the right, or it can go the other way. We don't know which way it's going to go. It's just going to go one of those two ways. Now, the current's got to be in the direction that opposes the change that causes it. That makes sense when you understand that the current that's induced will cause its own magnetic field. Now, that magnetic field on the left-hand side of the coil can either be a north or a south. If you were to look at the coil from the left-hand point of view, if it's going anti-clockwise or clockwise, that's going to produce a north or a south pole. Anti-clockwise produces a north pole. South pole is produced by a clockwise motion. You can kind of remember it by using those letters, which kind of curve in the right way. If you kind of squint a bit and look at them, a bit funny. So in this case, it's going to form a north pole on the left-hand side, anti-clockwise, to kind of repel the magnet that comes in. If I was to replace it with a south pole, it'd be the opposite. It would have a south pole repelling it, meaning the current would flow the opposite direction, which would be clockwise. All right, so this seems a little bit mental. Why is it that it kind of repels out the magnet that's trying to be pushed in? Well, if you think of the alternative, underlying everything in the world as we look at it is conservation of energy. Energy can't be made or destroyed. If you were to have, for example, in the south pole in this image, if you were to have a north pole inside the coil, what that would do is attract the magnet towards it. If you had a few of those, you'd be sort of creating energy. You just place the magnet very, very slowly towards the coil, and it would just speed up, and you could have hundreds of them, and it could speed to really, really high speeds without putting any energy in at all. So the alternative is you create energy. So we have to basically oppose it. And it's kind of a bit of an example of Newton's third law, if you think of it like that, if that helps you to understand it. One of the best examples of it is, you might have seen this demonstration, a copper tube, a magnet being dropped through it. So what happens is the magnet kind of drops through the copper tube. It slows down. I've got a little GIF here to help kind of show what that looks like. So what happens is the magnet, as it's going down, causes these very small electrical currents to flow in the copper tube, and they flow in the direction that opposes the magnetic field that caused it, or the change that caused it. So, for example, if it's a north pole goes in first, they're going to make a little north pole to repel it. If it was a south pole that goes in first, it's going to be a little south pole to repel it. That's all well and good, but being able to produce current to flow in one direction or another is not particularly useful. So let's have a look at how generators are constructed to make current flow in a kind of sustainable way that's useful to use in power stations, etc. So inside a generator, it looks very similar to our diagram from earlier, apart from now we've got a coil of wire that's going to be turned through magnetic field. And we're going to keep an eye on Faraday's law. It's going to help us understand the factors that are affecting the EMF induced. Right, so you do have to use your imagination a little bit with this one. You've got to imagine the coil being kind of turned through, so 9 degrees, 180 degrees, etc. So let's take each situation at a time. So initially, the coil is parallel to the magnetic field. Now that's where the maximum EMF is going to be induced. I'll explain why in a second. Next one is perpendicular. It's going to be zero EMF. Then it's going to be kind of parallel, but sort of the other way around, the other side. Then you're going to have the maximum EMF in the negative direction. And then you can have the same zero when it's perpendicular, and so on and so forth. So overall, you get this sort of nice wave formed on the screen, which in this case is a cosine wave. It will normally be a sine wave depending on where the motor starts from. So it's really important we look at why this is the case. So it's electromagnetic induction. Now I've got Faraday's law down on the bottom left side here. So when it's perpendicular, even though it's crossing a lot of field lines, Faraday's law is all about the rate of change of flux. Now, the change occurs the most actually when it's parallel. So if you were to imagine it sweeping through when it's perpendicular, even though it's got a large area, the area isn't really changing that much. It's pretty constant as it kind of rotates, sort of almost vertical, then a bit past vertical. It's going to have the minimum change in magnetic flux near that vertical point. Next, if we look at it when it's parallel to the field, so same setup, but this time the coil is kind of parallel, even though it's only sweeping through, like here, it's only one field line, that change is going to be the biggest because it's going to be sweeping through quite a change in them quite quickly. So that's going to mean you're going to have the maximum change in magnetic flux, even though actually the area is the smallest, because it's all about that rate of change. Now, the analogy I like to use to explain it is like the pendulum. If you remember the pendulum from earlier in the course, when the pendulum's at its maximum, it has no velocity, but it has a maximum acceleration because it's kind of slowing down, stopping, and changing direction. So it's kind of a similar sort of thing to that. All right, so I normally said this graph is a sine graph. So the equation to work out the EMF at any point is equal to the initial or the maximum EMF times by sine of omega t, where omega is equal to the angular frequency, which is 2 pi f. So 2 pi times the frequency of rotation, or 2 pi over t. Now, the maximum value this sine omega t can be is obviously 1. So that means the EMF, the maximum it can be is 1. So from Faraday's law, EMF is the rate of change of flux linkage. So what that means is for a flux linkage time graph or even a flux time graph, and you know the number of coils, that's going to represent the gradient. So that can help us kind of figure out, well, what's the EMF going to be at each point. So from this flux graph here, the maximum gradient is going to be where it's kind of sloping downwards and sloping upwards. That corresponds to when the maximum EMF is. When the EMF is zero, that's because there's no gradient on the flux graph, meaning it's kind of flatlined. So therefore, you're going to have zero EMF produced. The thing is that you could be asked about the area under a graph of EMF and time. So if we arrange that equation a little bit, the flux linkage is the area under an EMF time graph. Right, last thing with generators is the idea of back EMF, which is kind of another example, another application of Lenz's law. Right, so you got to follow this one closely, okay? I'll do my best to explain it. So when the coil spins round, it's going to induce current, which I talked about that already. That's going to be overall in one direction. However, there'll be some EMF produced in the slightly opposite direction. Now that happens because you've got a current of in the coil of wire in the magnetic field. That's going to produce its own very small magnetic field. Now, when that happens, that means the overall magnetic flux linkage is changing slightly. And like we said, due to Lenz's law, it's going to oppose the change that caused it. Right, a couple of things left to finish off this topic then. The first one is transformers. So drawing a transformer here, the general explanation for a transformer, how it works, is very, very, very similar to just the electromagnetic induction in general. So we've got a change in magnetic field produced around this primary coil, which is produced by alternating current in a coil around our iron core. That produces a changing magnetic field. That changing field passes through this iron core to our secondary coil on the right-hand side. So even without touching it, it's going to cause an alternating PD to be induced. And therefore, if it's connected to a circuit, you're going to have an alternating current be produced across the second coil as well. So let's have a look at the equations for a transformer. Now, you remember these at GCSE. Obviously, we're A-level now. We're going to try and derive them and not just kind of state them. We're going to look at where they actually come from. So they come from Faraday's law. So let's write out Faraday's law for each coil. So instead of EMF, we're going to talk about PD. It's the same thing in this case. PD is going to be the same thing as EMF. And this is the form the equation's given him. So across the secondary coil, the voltage across the secondary coil, Vs, is going to be equal to the number of turns times by the rate of change of flux. Across the primary coil, it's going to be exactly the same, apart from instead of the number of turns across the secondary, we've got the number of turns across the primary. The number of turns across the primary times by rate of change of flux. Now, this is the same for both coils because you have the same magnetic field across the left coil as the right coil. Now, if I was to divide those two things, that whole rate of change of flux term cancels, and we are left with, if we cancel everything down, we're going to have Vs over Vp, so the ratio in the voltages between secondary and primary is equal to the number of coils across the secondary and the primary ratio in the same way. And this leads to the overall relationship that the PD is proportional to the number of coils. So in this case here, I've got a step-down transformer, which is going to be used to obviously decrease the voltage to make things safe for domestic use. We should also remember, if it was step-up, it'd be increasing PD to decrease the current and to make it more efficient to reduce heat loss, etc. That hopefully you'll remember from GCSE. All that still applies here. Right, so that's equation number one. Equation number two is a bit different to what you might remember from GCSE, which is all about transformer efficiency. So assume your transformer is 100% efficient, the power in is equal to the power out. That means the current times PD of the primary coil is equal to the current times PD of the secondary coil. Now, nothing's 100% efficient, neither transformers, so we need to include efficiency in this equation. So overall, the efficiency is going to equal the power across the secondary coil divided by the power across the primary coil. So IS Vs over IP Vp times 100. Obviously, you want to make it a percentage. So that's our second equation, which is efficiency equals IS Vs divided by IP Vp. And usually you'll have efficiencies of quite high, but nowhere near 100%. So we need to modify that equation a little bit. All right, then let's talk about, to finish off, RMS, root mean squared current, and PD. So to understand this, we need to be really clear what direct and alternating PD are. So in the UK, the main supply comes out at a mean potential difference of 230 volts. If this was direct current, it would be 230 volts the whole time. So in alternating current, what does that mean? Does that mean its peak is 230 or something different? Well, it can't mean its peak is 230, because that means it also reaches minus 230, and everything in between, meaning its mean value is going to equal a PD of 0. That's not helpful, because no matter how high the peak voltage is going to always have a mean of 0. So a solution is something called root mean squared speed. It's a similar idea as you might have come across in ideal gases. The idea is that the mean is going to be 0. We've got to find another way of finding an average. So let me explain how we work out this thing called root mean squared speed. Let's say I've got a circuit here with an AC supply, or an alternating supply, and a heater. So we're going to derive this using the idea of this heating, this heater giving off heat. So using the equation power equals I squared R, the current's alternating in this case because it's an alternating supply going up and down. But because it's I squared R, no matter if it's negative, the overall power is always going to be positive, and can be shown in this graph like this. If we were to find the mean power of produced by the heater, we would just take half of that red line, basically. So kind of the average just being the mean, the total divided by 2, or the peak power divided by 2. So overall, an expression for the mean power is equal to a half times by the maximum current squared times by the value of the resistor we're heating across. The really wordy definition of how we define RMS current is that the RMS value of alternating current is the value of direct current that will give the same heating effect as an alternating current across the same resistor. So root mean squared, root mean squared current squared times the resistor is going to be equal to half. Don't forget that a value of half comes because the mean power has to be, the mean power is the peak power divided by 2. So half of the peak current squared times the resistor. We can hopefully see here that the two values of the resistor are exactly the same, so we can cancel those on each side. And we can look at, and we square root everything, so we can find out what the value for IRMS is, and that happens to be square root of half times by the peak current squared. Taking the kind of simpler approach, that equals 1 over root 2 times by the peak current. So that's a general relationship, which is in your equation sheet. To find the RMS current, you do the peak current divide by root 2, or times by 1 over root 2. So for our problem from earlier with our mains electricity, if you were to find the peak current, the RMS value would be 230. The peak current is actually 325. So that's the maximum, that's the maximum voltage, or PD, you can actually get from a UK main circuit, even though the average is 230. So that's our relationship for current. You can also use the same relationship for PD. Don't forget, PD is proportional to current, assuming a constant resistance. So it's exactly the same thing for current. So for PD as it is for current, where V0 is the peak PD in the same way that I0 was the peak current. One of the best ways of modeling radioactive decay is by using dice. So let's imagine we have some regular dice where the probability of each face landing side up is a sixth. And we're to take a large amount of them, let's say 100 dice, and we're to throw them. And each time the dice lands with a 6 up, we remove it from the pile because it has decayed. I'll start off with 100. I lose about a sixth after the first throw, and then a sixth of that number, a sixth of that number, and so on. And if we plot a graph, or results on a graph, they would look a little bit like this. So this is an analogy for radioactive decay, because radioactive decay is quite tricky to imagine and to understand. So if you ever get stuck, picture the dice, and it should make things make a bit more sense. So what's the definition of radioactive decay then? So radioactive decay is a random process, meaning that you cannot predict when an individual atom will decay. That being said, we usually don't consider one atom. We consider large samples of millions or billions or trillions of atoms. So for large samples, we can predict what percentage or what fraction will have decayed by a certain time. Now, this graph here is going to look very similar to the one I just drew with my dice. This time I'm going to have seconds on the x-axis, could be hours, could be days, whatever. And I'm going to have a number of nuclei remaining on the y-axis. Now, with a radioactive substance, the graph, decay graph would look a little bit like this. The defining features of this decay curve is that it takes the same amount of time to halve from 1,000 to 500, or from 500 to 250, etc. In physics, we call that the half-life. So the half-life is the time taken for the number of nuclei to decrease by half. It could also be the activity or the count rate to decrease by half as well, but we're sticking with number of nuclei here. So in this case, from the graph, hopefully you can see that's about an hour. If I was to find it for another set of coordinates, let's say 250 to 125, it should also be an hour. The curve isn't perfect here, so it's not going to work out perfectly for my graph. But that is the defining feature of what's called radioactive decay or exponential decay, is that it has a constant half-life. The time taken for the number of nuclei to decrease by half is the same. So if you ever get a question on this, always find an average. So do it from 1,000 to 500, then 500 to 250, 250 to 125, for example, and you should find they roughly are the same, and you take an average to find the average half-life. So this term exponential decay has a very specific meaning. It gets used quite incorrectly a lot in kind of popular culture, exponential growth, etc. Exponential decay or exponential decrease means that something, so the number of nuclei in this case, takes a constant or consistent amount of time to halve. Now, another more general way of defining exponential decay is by using the rate of change of nuclei. So let's say, for example, we denote the rate of change of nuclei with delta n over delta t. And what we say is that that is proportional to the number of nuclei remaining. Now, if we pause for a second just to think about this, this makes sense because the more nuclei you have remaining, that means the more of them you're going to lose every second. And the less of them are remaining, that means the less of them you're going to lose every second. So the first bit of the graph is going to have the highest rate of decay, and the lowest will be the gradient is shallowest. Now, there is a special term for this rate of decay or rate of change of number of nuclei, and that's called the activity. So the activity of a radioactive isotope is equal to the number of nuclei decaying or disintegrating per second. And it's measured in becquerels or BQ, and the SI base unit would be per second, or S seconds to the -1. So rewriting our expression from above, then activity we can now say is proportional to the number of nuclei. Any two things that are proportional, we can insert a constant in there. Now, this constant we use the lambda symbol for, no relation to waves in any way, shape, or form. This is known as the decay constant. And we do have a negative sign in there because it's always decreasing. So the rate of change is always negative. Now, we define the decay constant as the probability of a nucleus, so one nucleus, decaying in 1 second. If you look at the units on each side of the equation, we can find out that the units for the decay constant are also seconds to the -1. So this decay graph can be described by the exponential decay equation, which you see on the screen here, where n is the number of nuclei left after a certain time t, n naught is the number of nuclei left at the start or initially, and e is Euler's number to the power minus the decay constant times by the time taken, which you're looking at. So if you don't know Euler's number on your calculator, it's just the E symbol, and you have to do that to the power of whatever you're trying to find out when using your calculator. Now, the other expressions you can use, which are equivalent to this, are also activity. So the initial activity will be A naught instead of N naught, which I've written there. You could also use the mass of the substance, because mass is proportional to the number of nuclei. So the M equals M naught e to the minus lambda t. Now, the one that's given to you in your equation sheet is the N one, so we're going to stick with that one here. Now, if you're going to try and find the decay constant or time at any point, we need to get them down from where they are currently as an index. And how we do this is we need to make sure we know our log rules. So the main log rules to use in this topic is that if you want to get x down from the index of e, you'd need to take the natural logs of both sides. So ln, or natural log of e to the x, equals x. So if I simplify this expression a little bit first, like I've done here, and I put n over n naught on one side, if I take the natural log of that expression, so n over n naught, that equals on my right hand side negative the decay constant times by time, which I'm hoping you guys can see makes it a little bit easier to figure out what t is or what lambda is. Okay, so let's consider a case which we were looking at earlier, which is after one half-life. So after one half-life, that n over n naught expression is, in our case, going to be 500 divided by 1,000, because after one half-life, there's 500 nuclei left. There were 1,000 left initially. So it could be those two numbers. It could also be 1,000,000 over 2,000,000. It could be 1 over 2. And to get rid of our minus sign, because we can't have negative time, we can use another log rule. That log rule is that you have the natural log of x over y. That's the same thing as writing ln, or lateral log of x, minus natural log of y. Now, in this case, if I simplify this down to being 1/2 instead of 500 over 1,000, ln 1 subtract ln 2 is going to be the same thing as writing ln 2, because natural log of 1 is equal to 0. So you'll have 0 minus ln 2, giving you expression of minus ln 2. Now, the whole thing is negative, so minus times minus ln 2 is the same thing as writing natural log of 2. Divide by our decay constant, So next we're going to look at how I could find the decay constant from a graph. Now we're not going to use this graph here, but by taking logs of both sides, so ln n over n naught equals minus the decay constant times time. Another way of expressing that is that ln n minus ln n naught equals minus decay constant times time. And rearranging it slightly again, I can see that if I plot a graph of natural log of n versus time, then I can work out the gradient. The gradient of this graph is going to be minus the decay constant, and the y-intercept, so the term at the end, the plus c, is equal to the natural log of n naught, or the initial number of nuclei. So one of the big applications of radioactive decay is carbon dating. So carbon dating is a way of essentially measuring how old substances that used to be organic are. So for example, trees that have died, or people or animals, etc. So let's have a quick example of how you go about using this. So carbon dating, let's say there was a tree with 72% of its radioactive carbon-14 remaining. Now in a question they'll tell you something like the half-life of carbon-14 is about 5,760 years. So how would you work it out then? We don't have the number of nuclei or the activity, and we're asked to find the time. So what we can do is to use that to work out our decay constant, because we've got two unknowns for our exponential equation at the minute, and our half-life in seconds, we're going to put in seconds at the minute, which is equal to ln 2 divided by the decay constant. So putting our numbers in, we get our decay constant happens to be 3.82 times 10 to the power minus 12. And now normally decay constants are quite low, so that kind of makes sense. So now we know that, we're going to then put in our value for n over n naught and 0.72, take the natural logs of both sides, and then equal that to the decay constant times t. And then to find t, we're going to substitute our value we worked out earlier, which gives us a time taken, for the tree's age, which is 8.6 times 10 to the power 10 seconds. I've converted this to years, so divide by 60, divide by 24, divide by 365. So you might be able to notice you can actually, for a number of nuclei, you can keep the decay constant in years here. I've done it in seconds, then back to years, because if you're asked to use the activity version of the exponential equation, then that is going to be needed to be converted into seconds anyway. So another good use of radioactivity, there's loads of them. So radioactive tracers, other forms of dating like radiometric dating with uranium would be big ways you could be asked for the half-life of different radioactive substances. If the whole atom is the size of a football stadium, then the nucleus is the size of a pea to that scale. So how do we know this? In real life, the nucleus is around about 10 to the power minus 15 meters. But how do we know this? What evidence have we got? The first one was the Rutherford scattering experiment, which is how we know the nucleus exists in the first place. Then we're going to look at the idea of closest approach, so how close a charged particle can get to the nucleus without repelling and deflecting backwards. And the last one is electron scattering. So let's look at the Rutherford scattering experiment. So in 1913, the generally accepted idea was that the plum pudding model of the atom was true, meaning a big ball of positive charge with small negative charges distributed throughout. What we expect to happen was that the alpha particles Rutherford fired at the gold foil would all be undeflected, because they would go straight through. There's not enough charge in any one place to deflect them significantly. What he found, though, was slightly different. Most of the particles, the vast majority, followed this. However, some of them were deflected through small angles, and 1 in 10,000 were deflected by over 90 degrees. So in a small scale, looking at the results, something like this. So we can see here some of the particles going straight through, some of them deflecting back. This one will be by more than 90 degrees. This indicates there must be an electrostatic repulsion between the two positive charges, the positive alpha particle and the positive nucleus. So the electromagnetic force must be in play. And it affects all those particles that go close. The idea is the greater the force happens at a smaller distance, because force is inversely proportional to the distance squared, which we should know from Coulomb's law. So the conclusions Rutherford made from this then was that, well, there must be a nucleus, but most of the atom must be empty space. And the positive charge must be in the nucleus, which is extremely small, positive charge, which contains almost all of the atom's mass. And there must be these negative charges, the electrons around the edge, but we'll leave those for the time being. This became known as Rutherford's model, or the nuclear model of the atom, and it didn't describe how shells exist, it just described electrons as orbiting different distances away, but generally quite far away from the nucleus. And you had to wait till Niels Bohr, around 20 years or so later, to come up with the ideas of electrons existing in discrete shells. So this number here, the number of the particles that are deflected by over 90 degrees, leads us to our first estimate for the size of the nuclear radius. Now, considering the gold foil, let's say it's 1 atom thick, which obviously it's not, but it's an easy assumption to start out with. What that means is that these numbers state 1 in 10,000 deflect by 90 degrees. So therefore, if there were n layers, so 2 layers, 5 layers, 100 layers, we do 1 divided by 10,000 times n. So for n number of layers, we can do a quick derivation to kind of compare the diameter of the nucleus to the diameter of the atom. So the area of the nucleus divided by the area of the atom is equal to 1 over 10,000 n. Now, we know area from the kind of two-dimensional point of view of the particle hitting the nucleus is pi d squared over 4. So if I do the area of the nucleus, that's pi d, small case d, diameter of the nucleus squared over 4, divided by pi capital D squared over 4. So this still equals 1 over 10,000 n. Now, cancelling down, we notice that we can cancel down to find the expression for d, the diameter of the nucleus, which is big square root the diameter of the atom, divided by 10,000 n. Now, commonly, the number of atoms in Rutherford's experiment was around about 10,000. So we could kind of place that in place of n and come up with an expression for the ratio of d to d, diameter of the atom versus diameter of the nucleus, and it also equals roughly 1 in 10,000, meaning the scale is 1 to 10,000. Taking this one step further, we're going to look at the idea of closest approach to come up with a more accurate and more precise method and value for the radius of the nucleus. So let's consider an alpha particle heading towards the nucleus. Now, the most it can deflect by is 180 degrees, meaning it goes dead onto the nucleus, basically stops, turns around, goes the opposite direction. So when this alpha particle scatters an angle of 180 degrees. So when this happens, let's consider the energy changes that are occurring. So as the alpha particle is moving initially, when it's far away from the nucleus, it has maximum kinetic energy. When it stops and turns around, in that brief moment, its kinetic energy is 0. So by conservation of energy, that energy can't disappear. Where is that energy gone? Well, because the nucleus has a charge, all that kinetic energy is electrostatic or electromagnetic potential energy. So that potential energy is going to be maximum when the kinetic energy is 0, and then it decreases again when the alpha particle starts moving away from the nucleus. So let's put these two values together and let's kind of equate them. So kinetic energy is obviously half mv squared. The electrostatic potential energy, if you do AQA, it's not given to you on your equation sheet, but you do get given the value for potential. Now, the potential is equal to this constant 1 over 4 pi epsilon 0 times by the charge divided by r. And we know work done equals charge times potential difference. So therefore, we can kind of quickly derive the equation for potential energy is 1 over 4 pi epsilon 0, the two charges multiplied together, divided by r. If we equate these two equations together, it gives us an estimate for the radius of the nucleus, the distance from the center of the gold nucleus to the distance the alpha particle stops, turns around, and goes back. So let's plug some numbers in and see what we come up with. So let's take for the alpha particle scattering experiment, we've got the first charge is an alpha particle with 2 protons in it. Second charge is gold, which happens to have 79 protons in it. The mass of the alpha particle, we can add together the mass of 2 protons and the mass of 2 neutrons in your equation sheet. And we're going to say the speed here is pretty high for this experiment to yield accurate results. We can say it's 1.5 times 10 to the 7 meters per second. So let's solve this for r. So rearranging the equation, first of all, r equals 1 over 4 pi epsilon 0, q1, q2 over half mv squared. And we can put the 2 to the top of that equation to make it look a bit neater. Next is just about substituting our values in. So all the values from the left are on your formula sheet, the mass of the proton and the neutron as well. Or they're so similar here, you could just do 4 times the value of a proton. So putting all these numbers in together, and we come up with a value for r of 4.84 times 10 to the power minus 14 meters, which is fairly close to the estimate we talked about earlier. Now, things that will affect it is just an estimate because the speed of the alpha particles will affect it quite drastically. So if they're going slower, they're not going to get as close. And you aren't really finding the radius of the nucleus. You're essentially finding how close a charged particle can get before deflecting 180 degrees. But it's a fairly decent estimate for now. So let's have a look at electron scattering. So our final method of finding the radius of the nucleus. So we're going to fire electrons at atoms and use their wave-like properties to see their diffraction pattern, which is the quantum physics you will have learnt hopefully earlier in the course. So let's consider our electrons, which are behaving like waves. So we're going to draw them as wavefronts heading towards our material, which has a bunch of nuclei in it, all kind of regularly arranged as it's a solid. Because the gap is similar to the size of the wavelength, diffraction will occur, and we'll see a diffraction pattern if we were to have a screen installed at the other end. Now, it'll be a single slit diffraction pattern, just considering kind of in one spot with the electrons diffracting through one gap. We should know from our waves topic the diffraction pattern of a single slit looks a bit like this. You've got a really big, wide central maximum, then you've got smaller minima and maxima decreasing in intensity away from the center. Now, realistically, with this experiment, it's in 3D, so the diffraction pattern will look more like a set of rings rather than this kind of 2D image here. So the de Broglie wavelength, to which we need to make the electrons travel similar to investigate the diffraction of the atoms between the atoms, should be roughly 10 to the minus 15 meters. So to make that happen, the mass of the electron is obviously unchanged, so 9.31 times 10 to the minus 31 kilograms. The velocity needs to be, roughly speaking, 10 to the power 7 meters per second. So again, similar to the alpha particles from before, it's quite hard to get electrons and alpha particles to these speeds. This is why this is quite tricky to achieve. So what do we notice then? If the electrons do diffract, because the gaps between the atoms are roughly the same as the wavelength of the electrons. So you notice from the setup here, and this looks very similar to the Rutherford scattering experiment, apart from we're using electrons, but we've got detectors kind of all around the edge to see the intensity of the particles detected. And the particles will obviously diffract through different angles. So if we were to look at the intensity, using kind of Rutherford's scattering, we'd expect the curve to be a bit like this. Maximum would occur at 0 degrees angle, and then it would decrease the further away you get from that central part. However, if diffraction was to occur, the line would be slightly different. There might be some little bumps in it because of the different interference patterns we get. And this is actually what we observe. We observe Rutherford scattering, but kind of superposed on the top of it are the kind of maxima and minima we would get from an interference pattern. So we see the maximum there, the first maximum is when it's kind of raised up, and the minimum just next to it. So from this interference pattern, we can actually look at what angle that occurs at and see, well, what wavelength must the gaps between the atoms be to enable us to work out the radius of the nucleus. The general idea is that diffractions occur, and therefore the wavelength of the electrons must be similar to the nuclear radius. If you set up the electron's wavelength just right, then you can basically use that to work out exactly what the nuclear radius is. Now, there is an equation for this. It's not on the AQA spec. It is on other specs, which is to use the minimum, the angle the first minimum occurs at, to use this equation to work out the nuclear radius, which, like I said, it's not on the AQA spec, but it's useful to know how you'd go about doing that anyway. Okay, so those are our three methods of kind of estimating the nuclear radius. Next, we're going to look at is how it relates to nucleon number and how we can calculate the density of a nucleus. So consider one hydrogen nucleus, so one proton, and then I expand it to a helium nucleus. Hopefully, it's obvious that the radius is going to increase. So in this case, it doubles. So 2 protons means it's double the radius. However, the more protons and neutrons you add, that relationship won't hold. It's going to get bigger and bigger in a kind of form of a sphere. So we're going to look at how does a nuclear number affect the nuclear radius, and then how does it affect the density. The first thing to note here is that the nucleon number, the number of protons and neutrons, is roughly speaking proportional to the volume. So the nuclear number A, proportional to volume. Now the volume of a sphere is equal to 4 over 3 pi r cubed, so volume is proportional to r cubed. So using these two relationships, we can say nuclear number is proportional to r cubed. And stating that slightly differently, we can say a to the cube root. So stating that slightly differently, we can say the cube root of a is proportional to capital R, the radius of the nucleus. So any two things that are directly proportional, we can insert a constant of proportionality here. Now the constant in this case is R naught, which is usually estimated to be 1.05 femtometers, or 1.05 times 10 to the minus 15 meters. You won't be given this on your equation sheet for a couple of reasons we'll go into, but generally speaking, it is just an estimate. So more likely than not in a question, you'd be asked to calculate that first, or they'll tell it you in the question before you can use it. To work out R naught, you might be given a graph of cube root of A and R, and then work out the gradient of that to give you R naught, because it's R divided by the cube root of A. So to use this relationship, you just plug your numbers in once you've given R naught when you've calculated it. Now, what I think the coolest application of all this is you can work out the density of any nucleus using this idea here, using a bit of derivation. So to work out the mass of a nucleus, we need to know the number of nucleons times by the mass of each one. So we do nuclear number times by U atomic mass unit. Now, the volume of a nucleus, we said, is roughly speaking a sphere, so 4 over 3 pi r cubed. Now, instead of r down here, we're going to substitute in our equation r equals r naught and the cube root of a. So we're going to substitute that down here, and you might notice as soon as we plug that in, we can simplify things down quite neatly. I've got a third times by a cube, which is going to cancel down, meaning we've just got A on the bottom. We've also got A on the top, meaning we can cancel both those down and come up with our final expression for density, which equals the atomic mass unit divided by 4/3 pi r naught. Now, all of these things are constants, so don't depend on the radius of the nucleus or the number of nucleons. If you plug those numbers in, you get a value of 3.4 times 10 to the 17 kilograms per meter cubed. So the important thing about this is the same for any nucleus, okay? It doesn't depend on nucleon number, doesn't depend on radius at all. And it's insanely big, okay? 3.4 times 10 to the 17 kilograms per meter cubed is as dense as a neutron star, and basically means what you'd have if you managed to crush all the atoms down so there's no empty space in any of them. If we had like a millimeter cubed of this, so very, very small sort of grain of rice size, that would be basically 300 million kilograms just in a grain of rice, which is absolutely insane. Why are some isotopes radioactive but some are not? It's all to do with the idea of nuclear stability. So the atom itself can't think to itself, I need to decay. There are reasons why certain atoms and certain isotopes will decay by alpha, beta or gamma. And all atoms want to become stable. That's the big idea behind stability. They want to go from being unstable to stable nucleus, and they do that by decaying. But today we're going to look at why actually that happens. What we're going to do first of all here is plot lots of different isotopes and plot their proton numbers and their neutron numbers and see if we can see any patterns behind which ones undergo alpha or beta decay. So first line we're going to draw on is called the N equals Z line. Now that line is denoting basically isotopes and elements where they have equal numbers of protons and neutrons. So I'm going to label the stable elements in this purple color. Now if you plot these on, you'll notice at low proton numbers and low nucleon numbers, they are very close to the N equals Z line. For example, helium has an oxygen and carbon all have similar numbers of protons to neutrons in their stable forms. So this line carries on going upwards. It does get a bit above the N equals Z line, which means that those stable elements have more neutrons than they do protons. So that's our stable line first of all. Next we're going to look at beta minus emitters. I'm going to color these in hopefully a different enough color blue so we can see what happens. Now these isotopes all happen to be above the stability line, meaning they have even more neutrons compared to the number of protons in their nucleus. So this is a beta minus emitters. Right, next it's the beta plus emitters. We notice these are all slightly below that line of stability and closer to the N equals Z line, meaning they have slightly less neutrons per proton than most stable elements. Now last but not least are our alpha particles and alpha emitters. These are all very, very heavy, high proton numbers and high neutron numbers, but they're not in a line as say, they're kind of grouped in a cluster, sort of around about the sort of 80 to 90 proton number mark. So why did these atoms and isotopes decay in this way? Why is it that beta plus emitters are below the line of stability and beta minus emitters are above it? So to look at this, let's first recap what beta minus emission is, first of all. So beta minus emission in a nucleus, a neutron turns into a proton and a beta particle and also an antineutrino. So for that to happen, generally that's going to happen to neutron-rich nuclei, nuclei that have lots of neutrons in them compared to the number of protons, because they have these kind of spare neutrons to get rid of and turn into protons. Beta plus emitters are the opposite. So beta plus emitters, because the equation for beta plus decay is a proton changing into a neutron plus a beta plus particle or a positron and a neutrino, this occurs in proton-rich nuclei instead of neutron-rich nuclei. In alpha particles, which, like I said, are generally speaking kind of 60 and above protons, generally speaking, sort of 200 upwards of total number of nucleons. This occurs because alpha particle is quite a big particle. It needs to get rid of 2 protons and 2 neutrons. It needs a lot of them to begin with. So that's starting to explain this idea of nuclear stability, but to zoom in even further and to go even deeper, we need to look at what's actually happening inside the nucleus. So inside the nucleus, we might remember maybe from earlier in the topic or from year 12, stability depends on the balance of protons and neutrons due to the forces at play. So the forces at play inside the nucleus, you've got the strong nuclear force, versus the electromagnetic or electrostatic force. Now, the balance between these two forces is key to understanding why nuclei are stable or unstable. Now, when we've got two protons, these are affected by the electromagnetic force because they have a positive charge. However, as you might be able to imagine, neutrons aren't affected by it. The strong nuclear force affects both protons and neutrons. So this is why they play out slightly differently depending on how many of each you've got inside the nucleus. Now, the strong nuclear force has a very small range. We're talking 1 to 3 femtometers where it's attractive. You might remember the graph from the topic where you've got different ranges, and it's attractive at these sort of 1 to 3 femtometer ranges, repulsive if it's any smaller, and much bigger than that, it's really negligible overall. So what this means is, if a nucleus becomes too large, the strong force has too small a range, so has no effect at all really to hold it together, hence why nuclei are very small to begin with, and you don't find ones that are above a certain limit. Electromagnetic force, by contrast, has generally is stronger at those higher ranges, but if you've got too many protons compared to neutrons in the nucleus, you're going to have too much electromagnetic repulsion, which is going to be bigger than the strong force. So it's really all about these ratios of protons to neutrons that are at play with these types of atoms and how they decay. Gamma radiation, on the other hand, obviously doesn't involve protons and neutrons per se, but we need to know when that occurs and how that helps an atom become stable. So gamma radiation is emitted when a nuclei is what's called in an excited state, which is usually after alpha or beta decay. So in this example here, we've got magnesium, which is in an excited state. It's just undergone decay, and it's going to decay to aluminium. So after that, it's still in an excited state. So it's going to emit maybe 2 or 3 gamma photons to become less excited, to become more stable. So just like with electron transitions, it's the same sort of idea, but with nuclei, and that explains why gamma radiation is emitted by certain atoms. Now, the last level of kind of complexity with nuclear stability is the idea of decay series. So in a decay series, what it means is that, let's say you start off with uranium, it's unlikely you're going to have a stable element formed after just one decay. What's far more likely is that you'll have several happening at once. So we show these on our proton number, nuclear number graphs. Now for alpha decay, the proton number decreases by 2, so does the neutron number, so it heads downwards and left by 2 each way. If we're going to have beta decay, it looks slightly different because it doesn't lose the same number of protons and neutrons. So for beta minus decay, it heads downwards and to the right by 1 because we are gaining a proton but losing a neutron. Now, you do have to be careful with this. So some graphs will have, instead of the neutron number on the y-axis, they'll have the nucleon number. In this case, that means the number of nucleons doesn't change overall, so it should be a horizontal line to the right. So these decay series can go on for quite a while. Each change will have a half-life. It could be seconds, could be millions of years, and the uranium atom will keep going, decaying, alpha, alpha, beta, beta, for example, until it gets to something that's really stable. Now, in alpha's case, that happens to be lead, at which point it knows it's stable, so the decay series ends and it is stable.